Picture, if you willed, a sky not with one sun, but 12, a dozen brilliant spheres of fire tangled together in a silent, slow-motion ballet of unimaginable complexity. Some are locked in tight, whirling pairs, while others sweep in vast, stately orbits around each other. In this celestial arena, there is no true day or night as we know it, only an endless, shifting twilight where shadows are cast from a dozen different angles at once. This isn't a scene from a science fiction epic. This is the reality of a duodecuple star system, one of the most extreme and baffling arrangements of matter our universe has to offer. For centuries, astronomers believed such intricate systems were impossible, that the gravitational chaos would tear them apart in a cosmic heartbeat. The very existence of these stellar families defies our most basic intuitions about how the cosmos works, presenting a puzzle so profound it reshapes our understanding of stability, formation, and the very nature of existence on a grand scale. Today, we are embarking on a journey to the very edge of known astrophysics to explore 50 of the strangest, most mind-bending discoveries about these 12 star systems. We will uncover worlds where multiple suns chase each other across the horizon, creating sunrises and sunsets that are never the same twice. We will delve into the gravitational maelstroms that whip planets into bizarre, pretzel-shaped orbits and the violent stellar nurseries where stars are born in such dizzying numbers. This is a frontier of modern astronomy that is revealing secrets about the life and death of stars, the potential for habitable worlds in the most chaotic environments, and the fundamental forces that sculpt our galaxy. So prepare to have your perception of the universe stretched to its limits. We are about to venture into a realm of cosmic wonders that challenges everything we thought we knew, a place where the familiar rules of physics are rewritten and the sky itself is a canvas of perpetual, breathtaking motion. What we discover there might just change the way you see the night sky forever. The very idea of a star system with 12 members seemed, for the longest time, to belong firmly in the realm of theoretical fantasy. The gravitational equations told a grim story. With so many massive bodies tugging at each other, the system should tear itself to pieces in a relatively short amount of time, astronomically speaking. Yet nature had a surprise in store. The breakthrough came not with a single dramatic observation, but through a slow, painstaking process of piecing together a puzzle that spanned light years. Astronomers were using data from NASA's TESS mission, the Transiting Exoplanet Survey satellite, which is designed to hunt for planets by staring at stars and waiting for the tiny, periodic dips in brightness that occur when a planet passes in front of them. But in the data from one particular star, catalogued as TUI 703789-1, the signal was a mess. Instead of clean, repeating dips, the light curve was a chaotic jumble of eclipses with overlapping patterns that made no sense for a single star or even a simple binary. It was like listening to a symphony where a dozen different conductors were all trying to lead their own orchestra at the same time. To unravel the cacophony, scientists had to combine the transit data from TESS with another critical method, radial velocity measurements. This technique detects the subtle wobble of a star, the telltale tug from an unseen companion that causes the star to move slightly towards us and then away, shifting its light. When they applied this to TYC 703789-1, the wobble wasn't a simple back and forth. It was a complex dance, a signature that could only be produced by multiple stars orbiting in a tight, hierarchical configuration. The picture that emerged was stunning. The system is now understood as a stellar family of 12 stars arranged in a dizzying structure. Imagine 3 pairs of eclipsing binaries, each pair of stars locked in a close, frantic dance, whipping around each other every few days. Then 2 of these tight pairs are themselves orbiting each other, forming a quadruple system at the system's heart. This core is then orbited by the 3rd binary pair, and around this entire inner chaos, a final 3 pairs of stars sweep in much wider orbits. The initial reaction in the astronomy community was a mixture of profound disbelief and electrifying excitement. The discovery was published, and the paper essentially had to include a flowchart just to explain the system's architecture to its readers. The existence of TYC 703789-1 forced a complete re-evaluation of what is possible in stellar nurseries. Its very stability, despite the apparent chaos, hinges on this hierarchical principle, a cosmic version of divide and conquer. The stars aren't all pulling on each other with equal strength. They are organized into smaller, stable subgroups that then interact with each other at greater distances. This structure acts as a gravitational shock absorber, preventing the system from flying apart. Its discovery implies that the clouds of gas and dust that give birth to stars are far more dynamic and rich with material than we ever suspected, capable of fragmenting and collapsing into these incredibly complex, multi-tiered families. Finding one such system means there are almost certainly more, hiding in plain sight, waiting for us to learn how to listen to their complex, multi-voiced songs. With the architecture of a duodecuple star system now in mind, we arrive at the heart of the chaos, the gravitational environment itself. Think of our own solar system as a perfectly choreographed waltz, with planets following predictable, elliptical paths around a single, central partner. In a 12-star system, that elegant dance is replaced by a mosh pit. The gravitational pull doesn't come from one central point. It's a constantly shifting tug of war from a dozen different directions. This creates what scientists call an n-body problem, and for a system with this many n's, it is fundamentally unsolvable in the long term. We cannot write a single equation that will tell us precisely where every star will be in a million years. Their orbits are not neat, repeating ellipses. They are chaotic, meandering paths, sensitive to the tiniest of perturbations. A slight nudge from a passing star in one of the wider orbits can send ripples through the entire system, completely altering the trajectories of the inner binaries in ways that are impossible to forecast. This is a system living on a razor's edge of stability. This inherent orbital instability has dramatic consequences. One of the most startling is the phenomenon of stellar ejection. In this hyper-complex game of cosmic billiards, close encounters between stars are not just possible, they are inevitable over long enough timescales. When two stars in the system make a particularly close pass, their gravitational interaction can act like a slingshot. One of the stars might gain enough kinetic energy to achieve escape velocity, flinging it out of the system entirely and into the void of interstellar space. These ejected stars, known as runaway stars, become eternal wanderers, and their existence is a direct testament to the violent past of their birth clusters, which often include these complex multiple systems. So, a duodecuple system we observe today might not always remain one. It could be in the process of slowly dismantling itself, one gravitational encounter at a time. And what of any planets that might be brave enough or perhaps foolish enough to form in such a turbulent environment? Their fate is even more precarious. A planet's stable orbit depends on a consistent gravitational landscape, something this system utterly fails to provide. A close pass between two of the central binary pairs could easily disrupt a planet's path, sending it careening into the depths of space or on a collision course with another body. A planet might start its life in a relatively stable orbit around one pair of stars, only to be violently stolen by the gravitational pull of another passing pair, becoming a permanent wanderer with no true stellar home. The concept of a habitable zone, that Goldilocks region where temperatures are just right for liquid water, becomes almost laughable here. Such a zone would be in constant chaotic motion, shifting wildly as the various stars move closer and farther apart. A planet might be baked by 4 suns one millennium and frozen in the darkness between them the next, making the development of life as we know it an unimaginable challenge. Yet amid this gravitational pandemonium, stellar life and death take on a uniquely bizarre character. In the crowded stellar neighborhoods at the heart of a duodecuple system, a star's demise is rarely the end of its story. This leads us to one of the most dramatic discoveries, the existence of stellar zombies. In the cosmic calm of our own galactic neighborhood, a star like our Sun will eventually exhaust its nuclear fuel, puff off its outer layers, and settle down to a long, quiet retirement as a white dwarf, an Earth-sized ember of ultra-dense carbon and oxygen, slowly fading into a cold, dark crystal over billions of years. But place that same dying star into the frenetic environment of a 12-star system, and its retirement plan is violently rewritten. The key to this celestial resurrection is proximity and gravitational opportunism. In these systems, stars are often born with a wide range of masses. The most massive ones live fast and die young, exploding as supernova or collapsing into neutron stars, leaving behind their white dwarf siblings. Now imagine one of these white dwarfs, a stellar corpse, is part of a tight binary pair with a still living, puffed-up red giant star. The white dwarf's intense gravity begins to act like a cosmic vampire, relentlessly pulling hydrogen-rich gas from the outer atmosphere of its bloated companion. This stolen material doesn't just fall onto the white dwarf. It forms a seething, hot accretion disk around it, spiraling inward until it piles up directly onto the dead star's surface. For a long time, nothing dramatic happens. The dead star simply grows a new, unstable skin of fresh hydrogen. But beneath that skin, the conditions are becoming increasingly extreme. The white dwarf's surface is already unimaginably hot, and the pressure from the accumulating layers of stolen gas climbs relentlessly. Eventually, a critical threshold is crossed. The temperature and pressure at the base of this hydrogen layer become so astronomical that nuclear fusion, the very process that powered the star in its first life, reignites with cataclysmic ferocity. This is not the slow, stable fusion of a main sequence star, but a runaway thermonuclear explosion that rips across the white dwarf's entire surface. In a blinding flash, this stellar zombie detonates, becoming thousands of times brighter in an instant. To an observer light years away, it would appear as if a brilliant new star had suddenly flashed into existence where none was visible before. A nova event, literally a new star born from the corpse of an old one. But the story can become even more terrifying. If the white dwarf is particularly massive and its vampiric appetite is strong enough, it can continue to pull material from its companion until it approaches the Chandrasekhar limit, a critical mass of about 1.4 times that of our Sun. At this point, the internal pressure can no longer support the star's own immense gravity. The entire carbon-oxygen core of the white dwarf undergoes a final, instantaneous fusion, a deflagration wave that rips through it in a fraction of a second. The result is a Type Ia supernova, a titanic explosion so violent and so standardized in its brightness that it can outshine an entire galaxy. This is the ultimate zombie apocalypse on a stellar scale, a dead star, resurrected by its neighbors only to be utterly annihilated in a final, universe-shaking blast. In the dense stellar environment of a duodecuple system, where gravitational interactions constantly tweak orbits and push stars closer together, the conditions for creating these vampiric pairs and triggering these spectacular resurrected deaths are vastly more common than in the lonely expanse of single-star systems like our own. Yet, against all odds, planets do manage to form and survive in these chaotic realms, and their orbital paths are among the most bizarre discoveries in all of astronomy. We have to completely abandon our single-sun perspective to understand them. In a duodecuple system, a planet isn't just orbiting a star, it's navigating a gravitational labyrinth, and this gives rise to several distinct, mind-bending orbital possibilities. The first is known as an S-type orbit. Here, a planet forms in a tight, close embrace around a single star or one member of a tight binary pair. In this configuration, the planet's primary gravitational master is its host star, and the other 11 stars in the system are merely distant, brilliant kings in the sky, providing light but having little direct gravitational influence on the planet's immediate path. For a planet in an S-type orbit, the concept of night might not exist at all. With so many suns scattered across the heavens, at least one would likely be above the horizon at all times, casting an eternal, multi-directional twilight. Then there is the P-type orbit, which is where the true cosmic weirdness begins. In this scenario, a planet doesn't circle a single star, but instead orbits the center of mass of 2 or even more stars locked in a tight dance. Imagine a world that orbits a pair of suns that are themselves whirling around each other every few days. From the planet's surface, these two suns would perform a mesmerizing celestial ballet, sometimes merging into a single, elongated blaze of light, other times separating to chase each other across the sky. But in a duodecuple system, a P-type orbit could be far more extreme. A planet could, in theory, find a stable path that encompasses the entire central quartet of stars, a place where 4 suns rise and set in a complex, ever-changing pattern. The sky would be a canvas of shifting constellations of fire, with stars of different colors and brightnesses weaving in and out of proximity. But the most profound consequence of these orbits is the chaotic nature of the so-called habitable zone. In our solar system, this zone is a relatively static, donut-shaped region where water can remain liquid. In a 12-star system, this zone is a shape-shifting phantom. For a planet in a wide P-type orbit around the system's core, the habitable zone wobbles and pulsates as the central stars move closer together and farther apart. The planet could experience periods of intense, multi-sun heating that boil away its oceans, followed by long, deep freezes as it finds itself on the outer edge of the gravitational dance, receiving only a faint trickle of warmth from distant pinprick suns. For a planet in an S-type orbit around a single, dim star, its chance for habitability could be suddenly and violently revoked by a close pass from a much brighter, hotter stellar companion, flooding the world with lethal radiation and heat for centuries before receding again. The very idea of a stable climate, a prerequisite for life as we understand it, becomes a fleeting and improbable condition in such an environment, a temporary calm in a perpetual storm of celestial motion. One of the most spectacular consequences of this stellar crowding is the phenomenon of eclipse chains, a celestial light show of such complexity that it defies easy description. From the hypothetical surface of a planet in a stable P-type orbit around the system's core, the sky would be a theater of perpetual motion, and the concept of a simple sunrise or sunset would be rendered utterly obsolete. Instead, the observer would be treated to a non-stop ballet of occultations as the dozen stars, each on their own unique orbital path, constantly pass in front of and behind one another. An eclipse in our solar system, whether of the Sun by the Moon or of a moon by Jupiter, is a rare and precisely predictable event. Here, eclipses would be a routine, near-constant feature of daily life. The nature of these eclipses would be wildly diverse. A close binary pair whirling around each other every few days would produce rapid, rhythmic dimmings, a flickering of the heavens as one star repeatedly ducks behind its partner. But the true spectacle would be the grand multi-star eclipses. Imagine the 2 brightest stars in the central quadruple system beginning to converge in the sky. As they draw closer, their light would merge into a single, brilliant supersun, casting sharp, overlapping shadows. Then, a third, fainter star on a different orbital plane would slowly drift across this combined beacon, plunging the world into a deep, coppery twilight for hours or even days as it blots out the primary sources of light and heat. This wouldn't be the sudden, dramatic darkness of a total solar eclipse on Earth, but a gradual, eerie fading where the sky remains illuminated by the other, more distant suns, creating a perpetual, multi-hued dawn or dusk on the horizon. The patterns of light and dark would be chaotic and unpredictable over long periods. There could be stretches of time, perhaps lasting for years, where the orbital alignments are such that at least 3 or 4 suns are always visible, creating an endless day where the planet is baked from multiple angles. This could be followed by an era of frequent, deep eclipses where the primary suns are often hidden, leading to extended periods of global cooling and darkness, broken only by the faint colored light of the remaining uneclipsed stars. For any potential life, this would necessitate unimaginable adaptations, organisms that could hibernate through the long, cold shadows and erupt into frantic activity during the brilliant multi-sun days. The very rhythm of life would be set not by the rotation of a planet, but by the complex, overlapping symphonies of a dozen different stellar orbits. For astronomers, these eclipse chains are both a computational nightmare and an unparalleled scientific treasure. Modeling the light curve of a duodecuple system is one of the most demanding challenges in all of astrophysics. It requires supercomputers to calculate the gravitational interactions between 12 massive bodies and then, for each microsecond of simulated time, determine which stars are eclipsing which from the perspective of a given point in space. The resulting theoretical light curve is a jagged, chaotic line, a seismograph reading of celestial pandemonium. Yet, by comparing these monstrously complex models to the actual, observed light dips from telescopes like TESS, scientists can perform a kind of cosmic forensics. Each eclipse, its depth, duration, and shape, reveals exquisite details about the stars involved. A gradual dimming and brightening indicates a star with a diffuse, gaseous atmosphere. A sharp, clean cut-off points to a star with a well-defined edge. The precise timing of the eclipses allows for the most accurate possible measurements of the star's orbits, masses, and sizes. In essence, the constant eclipses act as a natural, automated laboratory, probing the physical properties of each star in a way that would be impossible in a more placid, solitary system. The very chaos that makes these systems so intimidating to study is also what makes them such rich sources of data, offering a detailed census of an entire stellar family from thousands of light years away. The constant gravitational jostling in such a densely packed stellar neighborhood sets the stage for one of the most violent events in the cosmos, direct stellar collisions. While space is overwhelmingly empty and stars in typical galaxies pass each other like ships in a vast, dark ocean, the rules are completely rewritten inside a duodecuple system. Here, the average distance between stars can be hundreds or even thousands of times smaller than in our own galactic backyard. Over billions of years, the subtle, cumulative tugs from so many neighbors can gradually perturb orbits, twisting stable paths into intersecting ones. The chaotic nature of the gravitational interactions means that predicting a collision is nearly impossible. But statistics tell us that in such a crowded environment, it's not a matter of if but when. When two stars are destined to meet, their final dance is both terrifying and majestic. They don't simply crash like two solid billiard balls. In the final moments of their approach, their immense gravitational fields begin to violently distort each other's shapes, pulling vast streams of superheated gas into spiraling bridges between them. The tidal forces become so extreme that they rip the stars apart from the inside long before their cores make contact. When the stellar cores finally plunge together, the release of energy is cataclysmic. For a brief, spectacular moment, the collision can outshine every other star in the system combined, releasing more light than our Sun will over its entire 10 billion-year lifetime. This isn't just a bright flash, it's a fundamental restructuring of matter, forging a new, more massive star from the wreckage of the old. This cosmic forge is the primary birthplace of a class of stars known as blue stragglers. These are stellar anomalies that appear paradoxically young and hot, straggling behind their older cluster mates in their evolution. In a duodecuple system, the collision and merger of two older, lower mass stars provides a perfect explanation. The merger injects a massive infusion of fresh hydrogen fuel into the new star's core, reigniting nuclear fusion with a ferocious intensity and effectively resetting the star's evolutionary clock. The result is a massive, blue, and brilliantly luminous star that stands out starkly against its aging siblings, a stellar phoenix born from a violent union. However, the stakes can be far higher than creating a blue straggler. If the colliding stars are both extremely massive, or if the merger involves the remnants of dead stars, the outcome can be a phenomenon that ranks among the most powerful explosions in the universe since the Big Bang, a gamma-ray burst. Imagine the collision of two neutron stars, the ultra-dense cores left behind after supernova explosions. As these city-sized objects of pure neutronium spiral together, they emit gravitational waves and rip each other apart, spraying a soup of neutrons and radiation into space. This triggers a rapid series of nuclear reactions, creating a titanic jet of energy focused into a narrow beam. If one of those beams were pointed anywhere near a planetary system light years away, the effect would be apocalyptic. The flash of gamma rays and X-rays would effectively sterilize the daylight side of any world in its path, stripping away atmospheres and triggering mass extinctions. A single such event in a duodecuple system could reset the potential for life across multiple planetary bodies in a single, terrifying instant. The aftermath of a stellar collision or merger sends shockwaves both literal and gravitational through the entire system. The sudden disappearance of two stellar masses and the birth of a single new one creates a gravitational vacuum. The intricate balance of forces that held the system's hierarchy in place is violently disrupted. The new, more massive star now exerts a stronger pull on its immediate neighbors, potentially destabilizing tight binary pairs or altering the orbits of the wider stellar companions. It's like suddenly replacing one pendulum in a complex, multi-pendulum clock with a much heavier weight. The rhythm of the entire mechanism is thrown into disarray. The system must find a new equilibrium, a process that can take millions of years and may involve further close encounters, ejections, or even trigger additional mergers in a cascade of cosmic chaos. A single collision doesn't just create a new star, it rewrites the gravitational history of the entire stellar family for eons to come. And so we come to the most fundamental puzzle of all. How does a universe that seems to favor simplicity end up building something as baroque and complex as a 12-star system? The process of star formation, even for single stars like our Sun, is a delicate balance between the inward crush of gravity and the outward push of gas pressure and magnetic fields. To create a duodecuple system, this process must go into overdrive, operating on a scale of both size and chaos that stretches our models to their breaking points. Astronomers are currently piecing together this cosmic origin story, and the leading theories point to two very different yet equally dramatic pathways. The first is a story of a single, spectacularly fertile birth cloud. Imagine a molecular cloud core, a vast cocoon of cold gas and dust, but one that is far more massive and turbulent than the one that gave birth to our solar system. As this colossal cloud begins to collapse under its own weight, it doesn't do so smoothly. Instead, it fragments, shattering like a pane of glass under stress. Regions of higher density within the cloud rapidly become their own gravitational centers, pulling in material and condensing into the seeds of new stars. In a typical stellar nursery, this process might create a handful of stars, but in the case of a duodecuple system, the fragmentation must be exceptionally prolific, producing a dozen stellar embryos all at once, and crucially, in a configuration that is already hierarchical. The cloud's initial spin and complex magnetic fields could act as a blueprint, ensuring that the first fragments to form are tight binaries, and that these pairs then naturally fall into orbit around each other, building the system from the inside out like a set of cosmic nesting dolls. This monolithic collapse theory elegantly explains why the stars in a system like TOC 703789-1 are all roughly the same age. They are literal siblings born from the same parent cloud in a single tumultuous event. However, this theory faces a monumental challenge: avoiding immediate self-destruction. The gravitational potential energy released during the collapse of such a massive cloud is staggering. As the dozen protostars condense, they would begin to violently tug at one another, their orbits chaotically intertwining. For the system to survive its own birth, something must act as a gravitational stabilizer. Some scientists propose that the immense shared envelope of leftover gas from the parent cloud is the key. This primordial nebula swirling around the newborn stars creates a powerful drag force. It acts as a cosmic buffer, absorbing the excess energy of the most wildly orbiting stars and gently herding them into more stable, hierarchical paths before the gas eventually dissipates. Without this gaseous cushion, the stellar siblings would likely scatter to the winds, their family ties severed before they could even properly ignite their nuclear furnaces. The second major theory offers a more social and perhaps even more violent origin story: dynamic capture. In this scenario, stars are not all born together but are instead brought together. Picture a massively dense star cluster, a celestial metropolis where stars are packed thousands of times more tightly than in our own galactic neighborhood. In such a crowded environment, close encounters are commonplace. Here, the complex gravitational dance between 3 or 4 single stars can result in a fascinating outcome. Often, when 3 stars interact, the least massive one can be flung out at high speed, while the other 2 are left in a tighter, bound orbit, a process that essentially trades a wide, unstable trio for a stable binary and a runaway star. But sometimes the opposite can happen. A tight binary pair can swing past another binary, and through a complex gravitational exchange, the 2 pairs can become bound, forming a stable quadruple system. Over millions of years, this process of capture and binding could repeat, with single stars and smaller multiple systems being gravitationally snared by a growing central family, gradually assembling a 12-star system piece by piece, like building a sports team through aggressive recruiting. The capture theory has its own set of hurdles to clear. While it can explain the hierarchical structure, it struggles with the sheer efficiency required to build a system of 12. Most encounters in dense clusters tend to be disruptive, not constructive. Furthermore, the captured stars would likely have a wider range of ages and chemical compositions, as they were born in different parts of the cluster from different source materials. Observing the chemical fingerprints of the stars in a known duodecuple system could therefore be a crucial test. If they all share an identical chemical signature, it points strongly to a common origin in a monolithic collapse. If their compositions vary, it would be powerful evidence for a capture-based assembly. Currently, the data leans toward the monolithic model for systems like TOC 703789-1, but the truth may be a hybrid. Perhaps a core of 6 or 8 stars forms from a single cloud, and then, while still embedded in its birth cluster, it captures a few additional stellar strays, finalizing the count to an even dozen. The very existence of these systems tells us that star formation is not a single, simple process, but a spectrum of possibilities. And in the most extreme environments, the universe is capable of architectural feats of staggering complexity that we are only just beginning to comprehend. Now, let's turn our attention from the stars themselves to the worlds that might call this gravitational maelstrom home, or more accurately, attempt to survive within it. The chaotic orbits and close stellar encounters we've been exploring have catastrophic implications for any planets that form, giving rise to one of the most haunting discoveries about these systems. They are likely prolific factories for rogue planets. Imagine a young, hopeful world coalescing from a disk of gas and dust around a single star in the system. For a few million years, it might enjoy a relatively stable existence. But then, the predictable rhythm of its orbit is shattered. A close pass by another stellar pair, perhaps from the system's outer layers, sends a powerful gravitational shockwave through the neighborhood. For the planet, it's like being on a swing that is suddenly given a violent sideways shove. In an instant, it can be ripped from its gravitational moorings, its orbital velocity altered just enough to exceed the escape velocity of its parent star. Instead of a graceful curve, its path becomes an open-ended hyperbola, a one-way ticket out of the system. It is exiled, cast adrift into the frigid, lightless depths of interstellar space, becoming a rogue planet, a permanent wanderer with no sun to call its own. The scale of this ejection process is staggering. Computer simulations of dense multi-star systems suggest that for every planet that manages to cling to a stable orbit, dozens more may be violently evicted during the system's tumultuous early history. This means a single duodecuple system could be responsible for seeding vast tracts of the galaxy with these lonely, dark worlds. The fate of a rogue planet is a profoundly cold and isolated one. Without a nearby star, its surface plunges to temperatures only a few degrees above absolute zero. Any atmosphere it once possessed would freeze solid, falling as snow onto a landscape of eternal ice. Any potential for life as we know it is instantly extinguished, frozen in time. Yet these dark worlds are not necessarily dead. If a rogue planet is large enough, like a Jupiter analog, it could retain heat from its initial formation deep within its core for billions of years. In this scenario, a thick, insulating layer of hydrogen atmosphere might remain, and in a truly ironic twist, a subsurface ocean of liquid water could persist beneath a crust of ice, warmed by radioactive decay and planetary warmth. Life, in some extreme form, could theoretically cling to existence around hydrothermal vents on the ocean floor, utterly isolated in the darkness, never knowing a sunrise or a sky. But the gravitational chaos of a duodecuple system is a two-way street. Just as it can violently expel worlds, it can also act as a cosmic fishing net, capturing free-floating planets that happen to drift too close. The process is a gravitational mirror of the stellar capture we discussed earlier. A rogue planet wandering the void for millions or even billions of years might have its path fortuitously intersect with the outer reaches of the 12-star system. As it enters this region of intense gravitational influence, it encounters a complex web of pulling forces. A close pass by one of the wider orbit stellar pairs can act as a brake, bleeding just enough of the planet's kinetic energy to allow it to be captured into a wide, looping orbit around the entire system or one of its stellar subgroups. This captured world would be an orphan adopted into a massive, chaotic family, a world with a history utterly different from any planets that formed in situ. This leads to the possibility of a system containing a veritable menagerie of planets with wildly different origins. You could have one planet that is a native, born in a disk around a specific star. Another could be a captured interstellar wanderer, a world that formed around an entirely different star long ago and was ejected from its own birth system before being ensnared here. Their compositions could be starkly different, bearing the unique chemical signatures of their distinct stellar nurseries. A captured planet might be a carbon-rich world, a former gas giant whose hydrogen atmosphere was stripped away, leaving a surface of diamond and graphite. Another might be a water world, a globe covered by a deep, global ocean, frozen solid on the surface but potentially liquid below. The sheer variety of planetary types and histories that could be assembled through this process of capture and native formation makes a duodecuple system a potential museum of planetary evolution, showcasing specimens from across the galaxy, all held together in a single, dizzying gravitational embrace. Within this gravitational free-for-all, the very shapes of the stars themselves are not sacred. We often picture stars as perfect spheres of incandescent gas, their form dictated by the balanced struggle between the inward pull of gravity and the outward push of radiation pressure. But in a duodecuple system, that balance is constantly under assault from the outside. The immense shifting tidal forces generated by a dozen close companions act like a team of cosmic sculptors, relentlessly kneading and pulling at each star, stretching them into bizarre egg-shaped ovals. This is not a subtle effect. A star in a tight binary pair, for instance, can be stretched so dramatically that it resembles a luminous American football, with its long axis perpetually pointed toward its voracious partner. The constant deformation does far more than just alter its appearance. It fundamentally rewires the star's internal mechanics. Deep within the star's core, where nuclear fusion rages, the flow of energy is suddenly obstructed. The orderly process of convection, where hot plasma rises, cools, and sinks, is thrown into disarray by the star's distorted shape. This can create bottlenecks and turbulence, causing heat to build up in some regions and stagnate in others. One of the most dramatic consequences of this internal upheaval is the generation of monstrous magnetic fields. As the differentially rotating layers of the deformed stars shear against each other, they act like a colossal dynamo, amplifying magnetic fields to intensities far beyond anything seen in solitary stars. These fields, trillions of times stronger than Earth's, become trapped in the star's atmosphere, twisting and braiding into knots of unimaginable energy. And when these magnetic knots finally snap, the result is a stellar flare of apocalyptic proportions. Imagine an eruption that doesn't just represent a small fraction of the star's power, but one that can briefly double or even triple the star's total brightness in a matter of minutes. These superflares unleash tsunamis of X-rays and ultraviolet radiation that wash over the entire system. For any hypothetical planet orbiting closely, the effect would be devastating. A single such flare could scour away a planet's atmosphere, ionizing and blasting the gases into space, leaving behind a barren, irradiated rock. The constant barrage of this extreme stellar activity, driven entirely by tidal deformation, turns the entire inner sanctum of a duodecuple system into a shooting gallery of high-energy radiation, presenting yet another monumental barrier to the emergence and survival of life. Adding to the gravitational and stellar chaos is another, more subtle but equally bizarre feature of these systems: the strange fate of the dust and gas that forms the raw material for planets. In a calm, single-star system like our own protosolar nebula, dust grains had the time and tranquility to gently collide, stick together, and slowly build up from tiny particles into pebbles, then planetesimals, and finally planets, all within a serene, flattened disk. In a duodecuple system, this peaceful nursery is replaced by a Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter. The sheer number of radiation sources and stellar winds creates an environment of such intense and conflicting forces that the dust is sculpted into structures that defy simple classification, creating a true dust enigma. The primary disruptor is the cacophony of stellar winds. Every star, regardless of its size, emits a continuous stream of charged particles flowing outward from its surface. In a solitary star, this wind expands uniformly into space, forming a roughly spherical bubble. But when 12 stars are all blowing their winds simultaneously from different locations and with different intensities, the result is a chaotic battlefield of colliding shock fronts. The wind from a hot, massive Type O star is a hurricane of energy traveling at millions of miles per hour. When this hurricane slams into the gentler breeze from a smaller, cooler, red dwarf companion, it creates a wall of superheated, compressed gas and dust, a turbulent shock zone where temperatures soar and particles are accelerated to fantastic speeds. Within these violent interfaces, dust grains don't gently coalesce. They are sandblasted, shattered into even smaller fragments, or vaporized entirely back into their gaseous state. This constant bombardment acts like a universal grinder, preventing the initial, delicate steps of planet formation from ever gaining a foothold across vast swaths of the system. But nature abhors a vacuum, and it also finds opportunity in chaos. While these colliding winds shred dust in some regions, they can also act as unexpected sculptors, piling up material into dense, peculiar structures elsewhere. Imagine the gravitational focus of the system, the central barycenter around which the inner quadruple or sextuple stars whirl. The competing stellar winds from these central stars might create a relatively stable, though highly turbulent, shell around the entire core, a vast, porous bubble of dust and gas that contains the inner chaos. Meanwhile, in the quieter spaces far from the stellar mosh pit, the gentler winds from solitary stars in the wider orbits could carve out vast, hollowed-out cavities within the larger dust cloud, like bubbles within a cosmic foam. The resulting architecture wouldn't be a single, unified disk, but a fragmented and warped menagerie of rings, arcs, spirals, and shells, each with its own unique environment and potential for planet formation. This leads to one of the most counterintuitive discoveries. These violent conditions might actually catalyze planet formation in specific, sheltered pockets. Take, for instance, the region immediately surrounding a tight binary pair. The gravitational forces between the two stars can clear out a central cavity in their local disk, but just beyond this cavity, at the so-called snow line, where temperatures are cold enough for volatile ices to form, the situation changes dramatically. The shock waves from the colliding stellar winds of the binary can slam into this outer disk region, creating a sudden, intense wave of pressure. This pressure wave acts like a cosmic snowplow, sweeping up dust and ice particles into a dense, compact ring. In this concentrated pile-up, the collision rate soars. Particles that would otherwise glance harmlessly off each other are forced into contact, sticking together and rapidly growing into larger bodies. In this sense, the very turbulence that prevents planet formation on a grand scale can, paradoxically, create localized Goldilocks zones where the process is dramatically accelerated, potentially forging an entire generation of planets in a geologic blink of an eye. The composition of any planets that do manage to form in this environment would be profoundly strange. A dust grain's journey through the system would be a grand tour of extreme temperatures and radiation fields. A single particle might form in the cool outer disk of one star, be blown across the system by a stellar wind, zapped by intense ultraviolet radiation from a different star, and then finally be incorporated into a growing planetesimal in a completely different part of the hierarchy. This constant cycling would heavily process the dust, altering its chemical and crystalline structure. We might expect to find planets with bizarre, heterogeneous compositions, worlds that are a mishmash of materials from all over the system, their surfaces a testament to the chaotic mixing of their birth cloud. A single planet could contain ices forged in the frigid outer realms, silicates baked near hot stars, and complex organic molecules assembled in the turbulent shock fronts between colliding winds, making each world a unique and irreproducible artifact of systemic pandemonium. This extreme gravitational environment acts as a cosmic laboratory for stellar evolution, producing a collection of stars that often look nothing like the standard types we find in isolation. The forced proximity and frequent gravitational encounters essentially rewrite a star's life story, creating a population of stellar oddities that defy our standard classification charts. One of the most dramatic examples is the creation of overly massive main sequence stars. In a normal setting, a star's mass at birth dictates its entire life cycle, how brightly it shines, how quickly it burns its fuel, and how it ultimately dies. But in a duodecuple system, a star's initial mass is just a starting point. Through the violent mergers and collisions we discussed earlier, two medium-sized stars can slam together and combine into a single, much more massive object. Imagine two stars, each with a mass of 1.5 times our Sun, peacefully fusing hydrogen for millions of years. If their orbits are perturbed and they collide, the result is a new star with 3 solar masses. This newly forged star is an imposter in the cosmic census. It has the mass and brilliance of a young, hot blue star, but it's actually composed of the older, evolved material from its two predecessors. Its core is suddenly reinvigorated with a fresh supply of hydrogen, effectively resetting its evolutionary clock and granting it a new lease on life, albeit a much shorter and more turbulent one due to its increased mass. To an astronomer observing from afar, this star would stand out as a blue straggler, appearing anomalously youthful and energetic compared to its stellar siblings of the same true age. Its existence in the system is a permanent record of a past cataclysm, a living fossil of a violent merger. On the opposite end of the spectrum, the same gravitational forces that build up stars can also tear them down, creating stars that are paradoxically small and faint for their age. This process, known as gravitational stripping, often plays out in the tightest binary pairs. Picture a duo where a puffed-up red giant star is locked in a close orbit with a compact, dense companion like a white dwarf or a neutron star. The red giant, in its expanded state, has a very loose grip on its outer layers. The intense gravity of its dense companion acts like a cosmic peeler, relentlessly pulling this stellar material away. Over time, the red giant is systematically stripped down, layer by layer, until only its hot, dense helium core is left exposed. What remains is a stellar ember known as a subdwarf, a star that is far hotter and denser than a star of its low mass has any right to be. It's the stellar equivalent of having all your outer clothing torn away, leaving you shivering and exposed in a radically different environment. This subdwarf no longer fits the standard model of stellar evolution. It's a prematurely exposed core, a star that skipped the end of its normal life and was thrust into a strange, new phase by its aggressive neighbor. The stellar population in one of these systems can therefore look like a bizarre family portrait where no two members look like they belong together. The census might include a brilliant blue straggler shining with the stolen youth of its progenitors, a dim and ancient subdwarf that has been stripped to its core, a few perfectly normal main sequence stars that have miraculously avoided any major interactions, and the dense, dead remnants of stars that have already gone supernova. This menagerie of stellar types, all of the same age but in wildly different evolutionary states, provides astrophysicists with an unparalleled natural experiment. By studying them, we can understand the dramatic shortcuts and detours that gravitational encounters can force upon a star's life cycle, revealing pathways of stellar evolution that are simply impossible in the quiet solitude of empty space. Let's zoom out for a moment from the intricate details of orbiting dust and distorted stars and consider the grand, system-wide repercussions of this gravitational turmoil. One of the most dramatic and far-reaching outcomes is the creation of what astronomers call runaway stars. Within the crowded core of a duodecuple system, stars are constantly engaged in a high-stakes game of gravitational billiards. When two stars, or more commonly, a tight binary pair and a third single star, make an exceptionally close pass, the complex three-body interaction can have a spectacular result. Through a process known as the gravitational slingshot, one of the stars can be flung outward at an astonishing speed, sometimes exceeding 1,000,000 miles per hour. This isn't a gentle drift into a wider orbit. This is a violent ejection, a cosmic banishment where the star achieves escape velocity, breaking free from the gravitational bonds of its stellar family forever. These runaway stars become interstellar projectiles, shooting across the galaxy on solitary, never-ending journeys. Their discovery often presents a compelling mystery. Imagine astronomers observing a massive, young, blue O-type star speeding through a relatively empty region of space, far from any known stellar nursery. Such stars burn through their fuel so quickly that they only live for a few million years. They simply don't have the time to wander far from their birthplace. Finding one isolated and moving at high velocity is a red flag. It's like finding a single, still smoldering ember far from a campfire. The only logical explanation is that it was violently ejected from its source. That high-velocity star is a clue, a cosmic piece of evidence pointing back to a dramatic event in its past, most likely a chaotic gravitational encounter within a dense, complex multiple system that has since been disrupted. The legacy of these ejections is written across the galaxy. A runaway star doesn't travel alone. It can drag any orbiting planets along with it, dooming them to an eternal, sunlit but deeply frigid existence in interstellar space. Furthermore, if the runaway is a very massive star, its death can be a spectacularly misplaced event. It might travel hundreds of light years from its birthplace before finally exploding as a supernova, its shock wave rippling through a region of space entirely unprepared for such a cataclysm. The very existence of these stellar fugitives tells us that the serene star fields we see on a clear night are deceptive. The galactic disk is crisscrossed with the trajectories of these cosmic outcasts, each one a silent testament to the violent gravitational dynamics that occur within stellar families as complex and chaotic as a 12-star system. Now consider the view from outside this stellar maelstrom. If you were an astronomer aiming a powerful telescope toward a Duodecuple star system, you wouldn't just be observing the light coming directly from the stars themselves. You would also be seeing the fabric of spacetime around them, warped into a complex lens. General relativity tells us that any massive object bends the space around it, and a concentration of 12 stars creates a gravitational potential well of staggering depth. This turns the entire system into a multifaceted, naturally occurring telescope, one that can magnify and contort the light from objects billions of light years behind it. This phenomenon, known as gravitational lensing, is common with single, massive galaxies, but in a 12-star system, it becomes an unpredictable and kaleidoscopic spectacle. The lens is not a single, smooth curve. It's a chaotic mosaic of overlapping gravitational fields, each star contributing its own unique warp to the overall effect. The result is a celestial hall of mirrors, a single, distant galaxy situated directly behind the system from our viewpoint would not appear as one image. Its light, traveling toward us, would be forced to navigate the gravitational topography around the dozen stars. Some light rays would skirt close to one star, being bent slightly. Others would pass between two stars, experiencing a double dose of deflection. A third set might curve around the entire system. This splits the single source of light into multiple, distorted images, often stretched into long, luminous arcs known as Einstein rings. But with 12 lenses working in concert, the pattern wouldn't be a simple, elegant ring. You would see a fragmented, shimmering halo of galactic fragments, dozens of mirage-like copies of the same galaxy, each tracing a different path through the gravitational maze, arranged in a complex pattern around the central stellar family. It's as if you were looking at a disco ball, with each facet reflecting a different, warped version of the same background object. For cosmologists, this chaotic lens presents both a golden opportunity and a formidable challenge. On one hand, it acts as a tremendous natural magnifying glass. The lensing effect can amplify the faint light of incredibly distant galaxies, allowing us to peer further back in time than would normally be possible with our own telescopes. We could study the formation of the first galaxies in the universe in exquisite detail, all thanks to this cosmic lens. However, untangling the information is a computational nightmare. To understand what the background galaxy really looks like, astronomers must first create a precise map of the gravitational lens itself. This means building a model that accounts for the exact mass, position, and velocity of all 12 stars, a Herculean task given their chaotic orbits. Any slight error in the model results in a completely misinterpreted image of the background universe. It's like trying to discern the true shape of an object by looking only at its reflection in a funhouse mirror that is itself spinning and wobbling. This lensing effect also creates a profound complication for anyone trying to study the Duodecuple system itself. The light we receive from its individual stars is not necessarily a straight shot to our telescopes. The intense gravity of a star on the far side of the system can bend the light from a star on the near side, making the stars appear to be in slightly different positions in the sky than they actually are. Their apparent brightness can also be artificially boosted during precise alignments. This means that to understand the true architecture and properties of the system, astronomers must first subtract the effects of their own gravity on the light they emit. We are not seeing the system directly, we are seeing it through its own gravitational filter, a hall of mirrors where every piece of data has been subtly shifted and distorted by the very object we are trying to observe. This self-lensing adds an entire new layer of complexity to the already daunting task of mapping the orbits and characteristics of a dozen stars locked in a perpetual, chaotic dance. But the stellar fireworks don't stop at isolated superflares. The true, system-wide spectacle begins when one star's violent eruption becomes the trigger for a cascade of destruction, a domino effect of plasma and energy that can engulf the entire stellar family. Picture a massive flare erupting from a star in one of the system's tight inner binaries. This isn't just a flash of light, it's the catastrophic release of a star's twisted magnetic field, catapulting 1 billion tons of superheated plasma into space at near relativistic speeds, a coronal mass ejection of unimaginable scale. In our solar system, such an event from the Sun would be a major concern for our technology, but the vast emptiness of space usually gives planets time to react. In a duodecuple system, however, the next star over might be alarmingly close, perhaps only a few times the distance between the Earth and the Sun. When this projectile of magnetized plasma, traveling at millions of miles per hour, slams into the magnetosphere of its stellar neighbor, the collision is apocalyptic. The impact compresses the second star's protective magnetic field like a battering ram hitting a shield. The energy transfer is immense, dumping the kinetic energy of the entire coronal mass ejection directly into the star's outer atmosphere, its chromosphere. This is where the true tsunami is born. The sudden, localized injection of energy doesn't just create a hotspot. It launches a literal wave of plasma that races across the star's surface. This chromospheric tsunami, also known as a Morton wave, is a wall of heated and compressed gas that can be hundreds of thousands of miles high, traveling at speeds that can exceed 1 million miles per hour, circumnavigating the entire star in a matter of hours. Now amplify this phenomenon across the intricate web of a 12-star system. A single coronal mass ejection from one star doesn't just hit one neighbor. Its shockwave can propagate through the complex interstellar medium, a space already filled with the competing winds and magnetic fields of a dozen suns. This can create a chain reaction. The initial impact on star B triggers its own chromospheric tsunami, which in turn violently destabilizes its magnetic field, prompting it to unleash its own, even larger coronal mass ejection. This second amplified ejection then travels on to strike star C, and so on. The system can enter a feedback loop of stellar violence, a cosmic version of a nuclear chain reaction where each stellar explosion makes the next one more likely and more powerful. For any planets caught in the crossfire, the consequences are beyond comprehension. Their atmospheres would be subjected to a relentless, multi-directional assault, being stripped away by successive waves of radiation and particles from multiple stars, not just one. A planet might survive the first flare from its host star, only to be sterilized hours or days later by a secondary wave of destruction that originated from a star halfway across the system, a celestial ricochet of pure energy. And so we arrive at the most human of all our questions, the one that tugs at our curiosity whenever we look up at the stars. Could life exist out there? When we apply this question to the controlled chaos of a duodecuple star system, the initial answer seems to be a resounding, almost laughable no. The challenges are so profound they read like a list of apocalyptic scenarios. First and foremost is the radiation environment. We're not talking about the occasional solar flare. This is a constant, multi-directional assault. with up to a dozen stars, many of them flaring frequently due to tidal distortions. The space within the system is flooded with lethal levels of X-rays and ultraviolet radiation. Any planet orbiting close enough to be in a traditional habitable zone would have its atmosphere systematically ionized and stripped away, its surface baked sterile. There is no magnetic field strong enough to reliably deflect such an onslaught from so many angles for billions of years. Then there is the gravitational instability. A planet's orbit is its home, its foundation. But here, that foundation is constantly being kicked out from under it. The gentle, predictable rhythmic tug of a single star is replaced by a violent, unpredictable shaking from a dozen different gravitational sources. A world could enjoy 1,000,000 years of stable climate, only to have a close stellar pass send it spiraling inward toward its suns or outward into a deep freeze. The very concept of a year loses meaning when your orbital period is constantly being perturbed. This makes the development of the long-term, stable environmental conditions necessary for the slow, patient dance of chemical evolution toward life an incredible long shot. And finally, the temperature swings. In our solar system, Earth's climate is buffered by its atmosphere and its stable distance from the Sun. In a 12-star system, the available energy hitting a planet's surface is in a state of perpetual, chaotic flux. A world in a P-type orbit might experience summer when the central stellar cluster is at its most compact, blazing with the combined light of 4 or 6 suns, raising temperatures enough to melt lead. Then, as those same stars swing to the far ends of their orbits, the planet enters a winter so profound that its atmosphere freezes solid, falling as snow onto the surface. These aren't ice ages, they are planetary deep freezes, cycles of sterilization that would reboot any nascent biosphere over and over again. Yet, against this bleak backdrop, nature is a master of finding loopholes. If we shift our perspective from Earth-like planets to more exotic niches, a sliver of possibility emerges. The most promising candidate is not a planet at all, but a moon. Imagine a massive gas giant, a Jupiter-like world, that has managed to find a stable P-type orbit far enough from the system's chaotic core to avoid major gravitational disruptions. This gas giant itself acts as a shield for its orbiting moons. Its immense gravity and powerful magnetic field could deflect a significant portion of the lethal radiation, creating a protected shadow, a safe haven. On one of its large, icy moons, a world like Jupiter's Europa or Saturn's Enceladus life could potentially thrive, but not on the surface. Beneath a thick crust of ice, shielded from the radiation and gravitational chaos above, a vast global ocean of liquid water could persist, warmed not by sunlight but by the constant gravitational kneading from its host planet, a process known as tidal heating. In this eternal, dark abyss, the sky above is irrelevant. The dozen suns are unknown, their light unable to penetrate the miles of ice. The energy for life wouldn't come from photosynthesis but from chemosynthesis around hydrothermal vents on the ocean floor. Here, in the perpetual warmth and mineral-rich waters, ecosystems could develop completely independent of the cosmic pandemonium unfolding in the sky. For such life, the concept of a sun is meaningless. Its entire universe is the dark water and the volcanic heat from below. But what if we dare to dream of a world with a surface, a place where an organism could look up? The sky it would see is beyond our imagination. With so many suns of different colors and brightnesses, true darkness might be a rare occurrence. The cycles of light and dark would be governed by the complex orbital periods of the stars, not the simple rotation of the planet. There would be no single day, but a series of overlapping days, a symphony of light. The sunsets would be a layered spectacle. A bright orange star might dip below the horizon, only for a brilliant blue one to rise minutes later from a different direction, casting long, confusing shadows. The constellations wouldn't be fixed. They would be these suns themselves, constantly shifting their positions in a slow, multi-millennial dance. For life to survive on such a surface, it would have to be unimaginably hardy. Perhaps it would evolve a biology that is virtually indestructible, with multiple redundant DNA repair mechanisms to handle the radiation. It might develop a form of suspended animation, becoming dormant during the extreme temperature swings of the orbital cycles, only to reanimate during the brief, temperate epochs when the stellar configuration is just right. Its perception of time would be completely alien, operating on geological scales to match the slow chaos of its heavens. While the odds are vanishingly small, the sheer number of such niche environments that must exist across the galaxy means we cannot completely rule it out. The universe has a way of filling every possible ecological niche, no matter how strange, and a duodecuple star system, for all its violence, still offers a few bizarre, sheltered corners where the flame of life might, against all odds, flicker into existence. While we can never truly hear the chaos of a duodecuple star system, we can translate its invisible dynamics into a form our senses can perceive, a theoretical soundscape born directly from the mathematics of its motion. Imagine taking the orbital frequencies, the gravitational tugs, the rhythmic eclipses, and assigning each a specific musical note or tone. The result would not be a harmonious melody, but a sprawling, chaotic symphony of cosmic proportions, a sonification of pure orbital instability. At the heart of this symphony would be the deep, thrumming bass notes of the widest orbits. These are the slowest, most ponderous frequencies, the foundational hum of stars that take centuries or even millennia to complete a single loop around the system's core. They would provide a constant, low-level drone, the gravitational bedrock upon which everything else is built. Layered over this deep hum would be the frantic, staccato rhythms of the innermost eclipsing binaries. Each close pair of stars whirling around each other every few days would produce a rapid, percussive beat. The sound would be a sharp, metallic ticking, like a hyperactive metronome, as the stars periodically eclipse each other and their combined light dims and brightens. With 3 or 4 such pairs in the system, you'd have multiple, slightly out-of-sync rhythmic patterns overlapping, creating a complex polyrhythm that constantly shifts and evolves. Then come the mid-range tones, the singing strings of the system. These would be generated by the orbits of the larger subgroups, the quadruple and sextuple systems at the center. As these stellar families orbit their shared center of mass, their gravitational pull creates resonant frequencies. Think of a cello playing a long, sustained but wavering note, its pitch subtly rising and falling as the stars move closer and farther apart, their gravitational influence waxing and waning. The true character of this symphony, however, isn't in its individual parts, but in their dissonant interactions. This is where the chaos emerges. A close gravitational encounter between a star in a wide orbit and one in the core wouldn't just be a silent event in the data. In our sonification, it would be a violent, screeching glissando, a sudden, dramatic slide in pitch as orbits are perturbed and velocities change. The resonant frequencies would not stay in a harmonious relationship for long. They would clash, creating jarring beats and discordant harmonies that grate on the ear, a direct auditory representation of the unsolvable n-body problem. This soundscape would have no repeating chorus, no predictable refrain. It would be a composition in a state of perpetual, turbulent becoming, where themes are introduced only to be twisted beyond recognition or violently cut short by a stellar ejection, which in this sonic universe would sound like a final, explosive crash of a cymbal followed by sudden, echoing silence as that star's frequency vanishes from the mix. Listening to this symphony would be an unnerving experience. It is the sound of order constantly battling chaos, a beautiful yet terrifying noise that is the true voice of a gravitational maelstrom. But for all the light and fury we can observe, some of the most profound discoveries in these systems involve what we cannot see. Astronomers studying the intricate dance of a duodecuple family can perform a kind of cosmic accounting. By measuring the orbital speeds and distances of the stars, they can calculate the total mass required to hold the system together, the mass that gravity is telling them must be there. Then they add up the masses of all 12 visible stars, and in some of these systems the numbers don't match. The gravitational mass is significantly larger, sometimes staggeringly so, than the mass of all the stars combined. This is the missing mass problem, a ghost in the celestial machine that points to the presence of immense, hidden objects lurking in the darkness between the stars. One compelling explanation is that these systems are cloaking stellar mass black holes within their gravitational folds. Picture a black hole with the mass of 10 suns, the remnant of a massive star that lived fast, died young in a supernova, and left this gravitational singularity behind. In the chaotic environment of the system's birth, this black hole wasn't ejected. It found a stable, if dark, niche within the hierarchy. It could be orbiting silently as part of a wide binary pair, its presence betrayed only by the subtle, telltale wobble it imparts on its visible stellar partner. Or it could be drifting through the system's core, its immense gravity subtly shepherding the orbits of the inner stars, acting as an unseen conductor of the celestial orchestra. Its presence would resolve the mass discrepancy instantly, but finding it is like searching for a shadow in a pitch-black room. We might only detect its existence during rare, violent moments, if it tears a comet apart, creating a flash of X-rays, or if it begins to siphon material from a star that ventures too close, lighting up an accretion disk of doomed matter in a final, brilliant scream before it crosses the event horizon. Another possibility is a population of failed stars known as brown dwarfs. These are objects that formed like stars but never accumulated enough mass to ignite sustained hydrogen fusion in their cores. They are cosmic embers, massive planets, or tiny stars depending on your definition, glowing faintly with the residual heat of their formation. A duodecuple system could easily host a dozen or more of these dark, Jupiter-like giants, each one adding significant mass but emitting almost no visible light. They would be nearly impossible to spot directly against the glare of their brilliant stellar siblings. Their collective gravitational pull, however, would be substantial, tugging on the visible stars and contributing to the missing mass enigma. They represent the system's dark, cold underbelly, a population of massive worlds that never truly became stars, forever hiding in the brilliant light of their successful family members. Then there is the most exotic and most controversial possibility that these systems are naturally trapping and concentrating dark matter. This mysterious substance, which makes up about 85% of the matter in the universe, does not emit, absorb, or reflect light. It interacts with normal matter only through gravity. The incredibly deep gravitational well of a 12-star system, especially an ancient one, could act as a cosmic flight trap. Over billions of years, vast clouds of dark matter particles streaming through the galaxy could be captured and held by the system's intense gravity, forming a dense, invisible halo that permeates the entire stellar family. This halo would add a tremendous amount of mass without giving off a single photon of light, perfectly explaining the discrepancy. If this is the case, then studying the precise orbital anomalies in a duodecuple system could provide one of the most precise local measurements of dark matter's properties ever achieved, turning these chaotic stellar families into unique laboratories for probing the universe's deepest secret. The practical challenge of solving this mystery is immense. To pinpoint the cause, astronomers must map the gravitational field of the system with exquisite precision. They look for telltale distortions in the paths of the stars. If the hidden mass is concentrated in one location, like a central black hole, the inner stars will orbit faster than expected, and their paths will precess or wobble in a specific way. If the mass is distributed evenly in a dark matter halo, the effect will be more diffuse, influencing the orbits of the outermost stars most strongly. It's a painstaking process of elimination, a cosmic detective story where the culprit leaves only gravitational fingerprints. The very existence of this missing mass adds a final, profound layer of mystery to these already complex systems, reminding us that for all we can observe, the universe always holds its darkest secrets closest. Now, let's consider the monumental task facing astronomers who want to understand the individual personalities of these 12 stellar suns, their composition, temperature, density, and motion. Normally, the primary tool for this is spectroscopy, the art of splitting starlight into its constituent rainbow of colors and reading the fine, dark lines imprinted upon it. Each element in a star's atmosphere absorbs light at very specific wavelengths, creating a unique barcode, a spectral fingerprint that reveals the star's deepest secrets. But in a duodecuple system, this elegant science transforms into a spectral nightmare. You are not collecting light from one star, you are gathering the combined glow of a dozen different suns, each with its own unique spectral barcode. And each of those barcodes is constantly smearing and shifting due to the star's orbital motions. The result is not a clean set of lines, but a chaotic, overlapping messy spectral soup, where thousands of absorption lines from different elements, different temperatures, and different velocities are all blended together into an indecipherable stew. Imagine trying to listen to a dozen different songs playing simultaneously from speakers all moving around you at different speeds. The Doppler effect would shift their pitches up and down, and your brain would struggle to pick out a single melody. That is precisely the challenge with the light from this system. The spectral line for hydrogen that is stationary in one star is blue-shifted in a second star moving toward us and red-shifted in a third moving away, all while the lines for calcium and iron from other stars weave in and out of the confusion. It is the ultimate cosmic jigsaw puzzle, with the pieces constantly changing shape and position. Untangling this snarled knot of light requires some of the most advanced computational techniques in all of modern astrophysics. The process begins by creating a monstrously complex digital model, a virtual replica of the entire 12-star system. Astronomers must first input everything they already know or suspect, the estimated masses, orbits, and rough temperatures of each star, based on the eclipse data and the overall system architecture. Then they create a massive digital library of template spectra, the clean, unblended fingerprints for every possible type of star, from hot, blue O types to cool, red M dwarfs. The supercomputer's task is to find the one combination of 12 shifting template spectra that, when added together in just the right proportions and with just the right velocities, perfectly recreates the observed chaotic spectral soup. This is not a simple subtraction game. It's a multi-dimensional fitting process of staggering complexity. The computer essentially acts like a master chef, trying to reverse engineer a complex recipe by tasting the final stew. It makes an educated guess, generates a combined spectrum, and compares it to the real data. The fit is never perfect, so it tweaks the parameters: a little more of this star, a little less of that one. Shift this spectrum slightly to the left, that one to the right, and tries again. It performs this comparison millions upon millions of times, using machine learning algorithms to navigate the impossibly vast parameter space, slowly homing in on the one unique solution that minimizes the difference between the model and reality. When this Herculean effort succeeds, the payoff is breathtaking. It allows scientists to perform a virtual census of the entire stellar family. They can determine the precise spectral type and surface temperature of each star, revealing which are brilliant blue giants and which are faint red dwarfs. They can measure the star's rotational velocities by seeing how broad their spectral lines are. A rapidly spinning star smears its lines. Most importantly, they can perform detailed chemical analysis on each star individually, reading the abundances of elements like iron, carbon, and oxygen in their atmospheres. This final piece of data is the ultimate test for the system's origin story. If all 12 stars show nearly identical chemical compositions, it is the smoking gun that they all form together from the same parent cloud. Any significant differences would hint at a more violent assembly line history through capture. The spectral soup, for all its initial impenetrability, thus becomes the key to writing the definitive biography of each member of this celestial dynasty, proving that even the most overwhelming chaos can be decoded with enough patience and computational power. Yet even within this gravitational storm, there are moments of breathtaking precision, fleeting instances where the cosmos seems to take a perfectly synchronized breath. This is the phenomenon of orbital resonance, a delicate clockwork harmony that can temporarily emerge from the chaos. In our own solar system, we see simple versions of this. Jupiter's moons Io, Europa, and Ganymede are locked in a 1-2-4 resonance, meaning for every single orbit Ganymede makes, Europa completes 2 and Io completes 4. This rhythm is stable and enduring, but in a duodecuple star system, the resonances are far more complex, temporary, and astoundingly beautiful. Imagine the innermost quadruple group of stars. For a brief window of time, perhaps lasting only a few thousand years, a mere blink in cosmic terms, their orbital periods might align in a precise, complex ratio. One possible configuration could be a 4-6-3-2 resonance. In this celestial waltz, for every 4 orbits completed by the first binary pair, the second pair completes 6 orbits, the third star in the subgroup completes 3, and a fourth completes 2. The gravitational pulls between them would reinforce each other in a repeating, predictable pattern. During this ephemeral era, their motions would be mathematically intertwined, creating a stable gravitational scaffold amidst the surrounding pandemonium. You could almost set a clock by their positions, as their conjunctions and oppositions would occur at regular, calculable intervals. This synchronization acts as a powerful stabilizing force for that pocket of the system. The rhythmic gravitational tugs prevent wild orbital excursions, locking the participating stars into a cooperative dance that protects them from perturbing influences, even from the other 8 stars in the wider system. It's a natural feedback loop of harmony. The resonance begets stability, which in turn reinforces the resonance. For any planets nestled within this temporary gravitational haven, it would be a golden age of climatic stability. A world orbiting one of these stars would experience seasons and stellar cycles with a regularity it might never know again. A fleeting chapter of predictable warmth and light in an otherwise chaotic existence. But this cosmic harmony is inherently fragile. It exists on borrowed time, perpetually threatened by the very nature of the system it briefly governs. The gravitational influence of the other, non-resonant stars in the system acts like a constant, subtle background noise. Their distant tugs gradually inject tiny amounts of energy into the resonant configuration, perturbing the delicate balance. Over centuries or millennia, these minuscule nudges accumulate like grains of sand piling up on one side of a perfectly balanced scale. The precise orbital ratios begin to drift. A period that was once exactly 3/5 of another becomes 3.001/5, then 3.01/5. The perfect clockwork begins to develop a wobble. The breakdown is not gradual. The resonant state is a precarious equilibrium, and once it's perturbed beyond a critical threshold, it shatters suddenly and completely. The synchronized dance collapses into chaos. The gravitational scaffolding vanishes, and the stars revert to their true, chaotic natures, their orbits beginning to meander and drift independently once more. The temporary era of harmony is over, and the system returns to its default state of glorious, unpredictable turbulence. This cycle of temporary order emerging from and then dissolving back into chaos is a fundamental characteristic of complex gravitational systems, a reminder that even in the most extreme environments, the universe has a fleeting appreciation for a perfect, intricate rhythm. This intricate gravitational harmony, so delicately balanced, is perpetually vulnerable to the most violent event in a star's life cycle. The death of just one of these 12 suns wouldn't merely be a localized catastrophe. It would be a system-wide shock, a trigger for what can only be described as a supernova domino effect. Consider the most massive member of this stellar family, a brilliant blue giant burning through its fuel with reckless speed. After just a few million years, its core collapses, unable to support its own weight any longer. The resulting supernova explosion is a universe-altering event in its own right, but here its impact is magnified 1,000-fold. The first and most immediate blow is the loss of mass. In an instant, a star that contained the equivalent of 20 or 30 solar masses sheds over 90% of itself, blasting its outer layers into space at nearly the speed of light. The gravitational anchor that this star provided, a fundamental part of the system's intricate balance, simply vanishes. The effect is like suddenly cutting a crucial cable on a suspension bridge. The remaining 11 stars, whose orbits were carefully tuned to the presence of that massive anchor, are now flung into disarray. The star's closest binary partner, if it somehow survives the initial blast, now finds itself orbiting a ghost. The gravitational center it was tied to has disappeared, and the star is sent careening off on a new, unpredictable trajectory, becoming a projectile aimed at the heart of the system. Stars in wider orbits, which were tracing graceful ellipses around the combined mass of the core, now find their paths fundamentally altered. Their orbits may become wildly eccentric, plunging them into previously forbidden zones of the system, or they may gain enough velocity to be flung out entirely, adding to the population of runaway stars. The hierarchical structure, the very principle that granted the system its longevity, is dealt a crippling, perhaps fatal, blow. Simultaneously, the physical shockwave from the supernova arrives. This isn't a gentle push, it's a wall of energized matter and radiation expanding at a significant fraction of light speed. When this tsunami of force slams into the other stars, it acts like a cosmic sandblaster, violently compressing their atmospheres and stellar winds. For any star already on the verge of instability, perhaps a red giant with a degenerate helium core, or a white dwarf creeping toward the Chandrasekhar limit, this sudden, immense external pressure can be the final push over the edge. The shockwave compression could trigger helium fusion in a giant's core in a violent flash, or it could cause a critically massive white dwarf to collapse, inducing a second, entirely separate supernova explosion. One death begets another, a chain reaction of stellar annihilation. This cascade of destruction would fundamentally rewrite the system's architecture in a single, violent episode. The sudden injection of energy and the loss of multiple gravitational anchors could force the remaining stars into a new, volatile configuration. Tight binary pairs, their orbits now destabilized, might spiral inward and merge, creating new blue stragglers amidst the chaos. Alternatively, the entire system could fail to find a new equilibrium, its gravitational bonds irreparably broken. The once grand family of 12 could be reduced to a smaller, traumatized cluster of 6 or 7 stars, while the rest are scattered across the galaxy, their trajectories forever marked by this ancient communal cataclysm. The supernova domino effect is the ultimate reminder that in a duodecuple system, no star lives or dies in true isolation. Its life and its death are inextricably linked to the fates of all the others, a cosmic lesson in interconnected destruction. And just as the physical environment presents a nightmare for survival, it also creates a profound and perhaps insurmountable barrier for anyone attempting to reach out from within, a challenge we can call the interstellar communication conundrum. Imagine an advanced civilization having somehow arisen on a sheltered moon or within a deep planetary ocean, now turning its curiosity to the cosmos. Their first instinct, much like our own, might be to listen. They would build colossal radio telescopes and aim them at the heavens, hoping to catch a whisper from another world. But the symphony they would hear is not the gentle hiss of the cosmic microwave background or the hopeful silence between the stars. It is a roaring, shrieking cacophony of pure noise. The sheer number of active stars in their system means the background radio emission is immense and constant, a wall of static generated by the turbulent atmospheres and flaring coronas of a dozen different suns. Trying to pick a coherent, artificial signal out of this stellar roar would be like trying to hear a single, whispered conversation in the middle of a hurricane. This problem is compounded exponentially by the sheer variability of the radiation. The system isn't just noisy, it's chaotically noisy. A predictable, repeating signal from another civilization could be teased out of a steady background. But here, the background itself is constantly changing. A superflare from a nearby star could drown out all other signals for days, only to be replaced by the Doppler-shifted radio scream of a rapidly orbiting binary pair, its frequency sliding up and down the spectrum in a complex, repeating pattern that mimics an artificial beacon. This creates a signal processing nightmare of almost unimaginable scale. Any potential transmission they might detect would have to be filtered against 1,000 different natural sources, each with its own dynamic fingerprint. The very concept of a clear channel for interstellar communication may not exist for them. Their entire celestial neighborhood is a permanent, multi-source jamming device, effectively placing their system inside a cosmic radio shadow, not because signals can't get out, but because they are lost in the background glare the moment they are broadcast. Even if this civilization decided to become the broadcasters rather than the listeners, their task would be Herculean. To have any hope of their signal being distinguishable from the stellar noise, they would need to transmit with truly astronomical power, far beyond what would be required from a civilization in a quiet system like our own. They would need to focus their energy into a laser-like beam of incredible precision, aiming it during the brief, fleeting windows when the orbital paths of their suns created a relatively clear line of sight to a specific target star. Their entire communication strategy would have to be a dynamic, real-time calculation, accounting for the positions and radio outputs of all 12 of their stars, predicting flare events and navigating the shifting Doppler shifts. It's a level of astrophysical engineering that stretches the limits of the possible, turning a simple hello into a multi-generational project of staggering complexity. This cosmic isolation, imposed not by distance but by stellar cacophony, suggests that the most complex systems in the galaxy could paradoxically be among the most isolated, their potential voices forever lost in the brilliant, chaotic static of their own suns. From the surface of a stable world orbiting a star on the fringes of this cosmic family, the night sky would be a spectacle of unparalleled complexity, a grand celestial clock with a dozen hands all moving at different speeds. Our own ancient astronomers, like the Babylonians or the Maya, dedicated centuries to tracking the wanderings of 5 planets against the fixed backdrop of stars. But for a primitive civilization evolving under the glow of 12 suns, this challenge would be magnified beyond our comprehension. Their fixed stars would be anything but. Instead of a stable celestial sphere, their heavens would be a dynamic, 3-dimensional dance of brilliant points of light, each following its own mysterious path. The very first sky watchers would notice that some of these suns, the ones in the tightest binary pairs, would appear to flicker or pulse in a regular rhythm as they eclipse one another from the observer's viewpoint. Others would drift slowly against the background over years or decades, tracing complex loops and curves as they orbit the system's center of mass. This wouldn't be a simple puzzle. It would be the ultimate cosmological mystery, a riddle written in fire across their entire sky. The development of their early astronomy would follow a path we can scarcely imagine. Their first great intellectual achievement wouldn't be predicting an eclipse of a single moon by its planet, but rather untangling the rhythmic dimming of just one of their dozen suns. Decoding the light curve of a single eclipsing binary would be a monumental task requiring generations of meticulous record-keeping. They would have to isolate the precise period of one pair's dance from a sky filled with other, overlapping variations in brightness. Imagine their first successful prediction. the ability to announce that the brilliant blue star known as the Hunter's Eye would dim to half its brightness for precisely 6 hours once every 322 days. This would be a triumph on par with our Newton formulating the laws of gravity. Their concept of time itself would be deeply tied to these celestial cycles. Instead of a year based on a single orbit, they might have a multi-tiered calendar, short cycles for the inner binaries, grand cycles for the orbits of the stellar subgroups, and perhaps great cycles spanning centuries for the slow precession of the outermost suns. This celestial environment would inevitably shape their entire philosophy and mythology. In our history, the perceived perfection of the celestial spheres influenced ideas of divine order for millennia. For them, the cosmos would present a very different lesson, one of organized chaos, of beautiful complexity rather than simple perfection. Their pantheon might not consist of solitary gods, but of vast, intertwined families of deities, their relationships and conflicts mirrored directly in the motions of the stars. A close conjunction of 3 particularly bright suns might be seen as a celestial council, a time of great portent. The rare, deep eclipse caused by a faint star passing in front of a brilliant one could be interpreted as a god being veiled in mourning or retreating in anger. The stories they would tell around the fire wouldn't be about a single sun chariot crossing the sky, but about the endless, weaving dance of a dozen luminous beings, their relationships dictating the fates of those living below. Their fundamental understanding of reality would be built on a foundation of multiplicity and interaction, a stark contrast to our own historical focus on a singular central light. Yet, for all their potential intellectual advancement in pattern recognition, these ancient astronomers would be working with a fundamentally incomplete picture. Without the concept of a 3-dimensional universe or the tools to measure stellar distances, their cosmos would be a flat projection, a celestial canopy. They would have no way of knowing that the 2 suns that appear close together in their sky are actually separated by billions of miles, or that the faint, slow-moving star is actually a massive giant, simply located much farther away than its bright, rapidly moving companions. Their star charts would be maps of apparent motion, not true orbits, the deep, intuitive leap that some of their stars were actually other suns, and that their world was part of this intricate dance might never occur to them. Their entire cosmology could be an extraordinarily complex but ultimately flawed geocentric model, a Ptolemaic system of epic proportions with dozens of epicycles and deferents needed to explain the observed path. The true revelation, that they were not at the center of this celestial ballet, but merely occupants of a single seat in a vast gravitational theater, would be a revolution waiting for a technological age they might never reach, a secret held tight by the sheer, beautiful complexity of their own sky. Now imagine a star surrounded by a swirling disk of gas and dust, a natural nursery for planet formation. In a normal system, this material would steadily spiral inward, feeding the central star or coalescing into new worlds. But in the gravitational free-for-all of a duodecuple system, this orderly process is hijacked, transforming a simple disk into a chaotic, system-wide feeding frenzy. One star's potential planetary building blocks become a shared buffet for its entire stellar family, creating a bizarre cosmic merry-go-round where matter is constantly stolen, traded, and consumed. The gravitational pull from nearby stars acts like a team of celestial thieves, reaching into a neighbor's disk and siphoning off vast streams of material. This stolen gas doesn't fall directly onto the pilfering star. Instead, it forms a lopsided, spiraling bridge, a temporary river of raw material flowing through the void. This matter then settles into a new, unstable disk around the second star, which might already have its own disk. The result is a complex hierarchy of accretion, where a single stream of gas could ultimately feed 3 or 4 different stars in succession, a daisy chain of stellar consumption that links the entire inner system together. The visual spectacle of this process would be both beautiful and terrifying. Instead of neat, flat disks orbiting each star in isolation, the inner sanctum of the system would be filled with a tangled web of glowing, spiraling arms of gas. These streams would constantly shift and reconfigure as the stars move along their orbits, sometimes feeding one star generously, then pinching off as a gravitational tug from a different direction steals the flow and redirects it elsewhere. From within, a planet-forming disk would not be a serene, isolated environment. It would be a war zone. The gentle, inward drift of dust particles would be overwhelmed by violent shock waves as these external streams of gas slam into the disk's outer edge. This could trigger bursts of rapid planet formation in some regions, as the sudden pressure waves force particles to clump together, while simultaneously shredding and vaporizing nascent planets in others. The very composition of any world that manages to form would be a chaotic amalgamation, built from material that originated around several different stars, each with its own unique chemical history. This relentless gravitational pillaging has profound and contradictory consequences for stellar growth. On one hand, it can stunt the development of certain stars. A smaller, quieter star trying to peacefully gather material from its own local disk could find its food supply consistently cut off by a more massive, greedy neighbor. This star might be starved, remaining a modest red dwarf while its siblings balloon into brilliant giants. On the other hand, this process can lead to the creation of stellar gluttons. A star situated at a gravitational crossroads, where multiple streams of stolen matter converge, could experience fantastically rapid growth. It would gorge itself on this system-wide bounty, ballooning in mass far beyond what would be possible from its own private reservoir of gas. This could create a star that is anomalously massive and bright for the system's age, a cosmic opportunist that grew fat on the stolen wealth of its family. The stellar mass distribution in a duodecuple system, therefore, isn't just a result of the initial birth conditions. It's a dynamic, ongoing record of gravitational theft and opportunistic feasting, a testament to the fact that in this environment, no star's pantry is truly its own. But this stellar drama isn't just about gravity and light. It's also about invisible forces weaving a cage of energy around the entire family. Each of the 12 stars possesses its own powerful magnetic field, a vast, invisible structure that extends far out into space. In a placid, single-star system, this field forms a relatively orderly bubble, but here, these 12 individual magnetic bubbles are forced to coexist in a space that is constantly churning. The result is a phenomenon of staggering complexity, a single, system-wide magnetic field knot. Imagine taking a dozen separate balls of incredibly energetic twine, each one constantly moving and spinning, and trying to braid them all together into one single, monstrous tangle. That is the magnetic environment of a duodecuple system. The fields don't simply overlap, they violently interact, slamming into each other, twisting around one another, and reknotting themselves with every orbital pass. This creates a dynamic web of magnetic force lines that permeates the entire system, a labyrinth of invisible highways and roadblocks for charged particles. Electrons and protons ejected by stellar winds or superflares don't travel in straight lines here. Instead, they become trapped, forced to ride these twisting magnetic highways. They are accelerated to velocities approaching the speed of light as they are whipped around magnetic corners and funneled through regions where field lines suddenly snap and reconnect, releasing colossal bursts of energy. This process turns the entire volume of space within the system into a natural particle accelerator, far more powerful than anything we could ever build on Earth. Any object within this domain, whether a planet, a comet, or a spacecraft, would be perpetually bathed in an intense rain of high-energy radiation, a deadly mist woven by the tangled magnetic fields. For a planet with its own protective magnetic field, this cosmic particle storm would manifest in a sky of perpetual, overwhelming light. The charged particles spiraling along the system's magnetic knot would be funneled down onto the planet's magnetic poles, creating aurorae of such scale and brilliance that they would redefine the very concept of the phenomenon. Forget the gentle, shimmering curtains of green and red we see on Earth. These would be global, searing displays. The entire sky, from horizon to horizon, could ignite in a blinding, multicolored firestorm. The aurorae wouldn't be confined to the poles. During periods of intense magnetic activity, they could engulf the entire planet, casting sharp, dancing shadows even at the equator and turning night into a hallucinatory, psychedelic day. The light shows would be accompanied by a constant, deafening crackle of radio static as the atmosphere itself is ionized by the particle barrage. For any potential life on the surface, this would not be a beautiful spectacle but a lethal environmental hazard, a constant reminder that the sky itself is a weapon forged by the magnetic chaos of a dozen suns. This brings us to one of the most fundamental shifts in thinking required to understand these systems, the complete dismantling of the classic Goldilocks zone. In our solar system, this concept is beautifully simple. A single, donut-shaped region around our sun where the energy output is just right for liquid water to potentially exist on a planet's surface. It's a stable, predictable place, but transplant that idea into a sky dominated by a dozen different suns, and the entire concept shatters. The habitable zone here is not a static ring. It is a shimmering, shape-shifting phantom, a three-dimensional volume of space that breathes and contorts with the ever-changing positions of its many stellar masters. Consider the energy sources. A planet's surface temperature isn't dictated by one star, but by the combined and constantly shifting light of 12. Some are brilliant blue giants pouring out immense ultraviolet radiation. Others are dim, cool red dwarfs glowing with a faint crimson light. A planet's location in this stellar crowd determines its fate. If it's in a relatively wide P-type orbit around the system's core, its experience of warmth is in perpetual flux. When the central quartet of stars swings close together in their dance, their combined luminosity might be equivalent to 4 of our suns. The entire inner region of the system becomes a furnace, and the traditional habitable zone is pushed far outward. A world that was once temperate is suddenly scorched, its oceans boiling away into steam. Then, centuries later, as those same 4 stars reach the farthest points of their orbits from one another, their combined light dims significantly. The zone of potential liquid water now lurches inward, and that same planet, once boiling, is now locked in a deep global ice age, its atmosphere freezing solid on the ground. This transforms a planet's climate from a stable condition into a series of dramatic, episodic chapters. A world could spend 100,000 years as a lush, water-rich paradise, only to be plunged into a million-year-long winter of absolute sterility. Life, if it were to arise, would face a cycle of catastrophic bottlenecks. It couldn't follow a slow, steady evolutionary path. Instead, it would need to be incredibly resilient, capable of entering long periods of suspended animation, perhaps as hardy spores or deep-dwelling extremophiles, to survive the frozen or baked epochs, only to re-emerge and flourish with frantic speed during the brief, golden ages when the stellar alignment is just right. The very rhythm of biology would be tied not to the planet's rotation, but to the grand multi-millennial clock of the stellar orbits. The concept becomes even more complex for a planet in an S-type orbit, tightly bound to just one of the 12 stars. Here, the direct heat from its host might be stable, but it is at the mercy of its host's companions. Imagine a planet perfectly content orbiting a calm, sun-like star. Its orbit is stable, and its star provides a consistent level of warmth. But then, its stellar companion, a brilliant blue giant on a long, elliptical path, makes its closest approach. For decades, this second sun grows from a bright point of light into a searing rival to its host, dominating the sky and flooding the planet with intense ultraviolet radiation and heat. The planet's surface temperature soars not because it moved, but because the habitable zone around its own star was temporarily and violently invaded by another. Its climate is hijacked by a celestial neighbor, turning a stable environment into a temporary hellscape. This means that in a duodecuple system, the habitable zone isn't just a property of a single star. It's a collective, system-wide phenomenon, a fragile and fleeting consensus reached only when the majority of the suns are in a benevolent configuration. The search for life here isn't about finding a planet in the right place, but about finding one with the right timing, a world currently enjoying a habitable epoch in a cycle of cosmic extremes. But perhaps the most mind-bending consequence of this gravitational complexity is one that warps the very fabric of time itself. In a duodecuple star system, Einstein's theory of general relativity moves from a theoretical abstraction to a tangible, daily reality. The principle is simple yet profound. Gravity doesn't just bend space, it also slows down time. The stronger the gravitational field you're in, the slower your clock ticks compared to someone in a weaker field. In our solar system, this effect is minuscule. A clock on the surface of the Sun would run only about 66 seconds slower per year than a clock on Earth, a difference so small it's barely measurable. But in the deep, shifting gravitational wells of 12 intertwined stars, this time dilation becomes a significant and bizarre feature of existence. Consider the life of an observer on a planet tightly orbiting one of the inner binary pairs. This world is perpetually deep within the combined gravitational pit of two massive stars, a region of space-time curved to an extreme degree. For that civilization, time would flow at a noticeably slower rate. Now, imagine they are trying to communicate with explorers on a research station orbiting a solitary, outlying star in the system's distant reaches. That outer star resides in a much shallower gravitational well where space-time is far less curved. From the perspective of the outer station, the clock on the inner planet would appear to be running in slow motion. A signal that the inner planet sends once per their local second would be received at the outer station at a slower, drawn-out pace. A conversation between them would be plagued by a strange, relativistic lag. The inner planet's inhabitants would age more slowly, their years stretching out while the outer station's crew aged at a comparatively normal rate. Over centuries, a tangible age gap would open up between the two populations, all because of their different addresses within the same stellar family. This isn't a uniform effect across the system, it's a dynamic and chaotic one. As the stars move along their orbits, the gravitational landscape constantly shifts. A planet might spend part of its orbit close to the system's dense core, its time slowing to a crawl, and then swing out into the relative emptiness of space between the stars where its clock would speed up again. There would be no single, universal now for the entire system. Synchronizing clocks or planning interstellar meetings would be a logistical nightmare requiring complex relativistic calculations that account for the instantaneous positions and masses of all 12 stars. An event that was observed to last for 1 hour from a vantage point near a massive star might be measured as lasting an hour and several seconds from a position out near the system's fringe. This means that cause and effect, the very sequence of events, could appear to play out in a different order depending on where you are located in this gravitational maze. The system itself prevents any absolute agreement on the passage of time, making it a universe in miniature where Einstein's strange predictions are woven into the daily experience of any hypothetical inhabitants. Now let's step back and see the entire duodecuple system not just as a family of stars, but as a single, colossal entity, a cosmic recycling plant operating on an unimaginable scale. Every stellar wind, every planetary disruption, every supernova blast isn't just an isolated event. It's part of a continuous cycle of creation and destruction where material is constantly being mixed, forged anew, and redistributed among the stars. This means a planet forming today in this system might not be built from pristine, primordial gas, but from the atomic ashes of its long-dead predecessors. Imagine the stellar winds we discussed earlier, those relentless streams of particles flowing from each star. In this crowded environment, those winds don't just dissipate into nothingness. They collide, merge, and create vast, turbulent reservoirs of mixed gas, a celestial smog that fills the spaces between the stars. This isn't inert dust, it's a rich broth of heavy elements. A carbon atom blown off the surface of a dying red giant might be flung across the system, only to be swept up by the gravitational pull of a different star entirely, eventually becoming part of a new protoplanetary disk. The very iron in the core of a future planet could have been forged in the heart of a massive star that exploded as a supernova millions of years earlier, its ejected remains now drifting through this communal pool of raw material. This process of cosmic recycling fundamentally changes the nature of planet formation here. In a calm system like our own, planets form from a disk with a relatively uniform chemical composition, a snapshot of the local birth cloud. But in this Duodecuple recycling plant, a planetesimal's forming disk is a chaotic junkyard, accumulating bits and pieces from across the entire system. A single growing planetary embryo could accrete material that originated from 4 or 5 different stars, each with its own unique nuclear history. One layer of the forming world might be rich in silicon and oxygen from the wind of a sun-like star, while the next layer could be laced with rare elements like gold and uranium, atoms that could only have been created in the violent death throes of a supernova that occurred light years away in a different part of the system long ago. The planets that eventually coalesce are therefore palimpsests, their compositions recording the violent and varied history of their entire stellar neighborhood, not just their immediate parent star. This has a startling implication for the potential of life. We often think of the ingredients for life, like carbon, nitrogen, and oxygen, as being delivered to a planet after it forms by comets and asteroids. But here, those ingredients are baked into the very foundation of the world from the very beginning. The complex organic molecules, the very building blocks of life, could be synthesized in the turbulent shock fronts where stellar winds collide, and then directly incorporated into the next generation of planets. A world forming 1 billion years after the system's birth might be far richer in these vital elements than any of the first planets ever were, because the recycling plant has had time to enrich the shared reservoir. The destruction of older, perhaps life-bearing worlds through gravitational ejection or stellar engulfment isn't necessarily a dead end. Their shattered remains, along with the complex chemistry they may have hosted, get ground down, mixed into the cosmic compost, and eventually become part of new, promising worlds. In this endless cycle, death is not an end, but a prerequisite for a more complex and potentially richer new beginning. The idea of a phantom companion emerges from the meticulous work of celestial accounting, where the math of motion stubbornly refuses to match the census of light. Astronomers can plot the precise orbits of the 11 visible stars in a Duodecuple system, calculating the exact gravitational pull required to keep each one on its observed path. Yet, when they add up the collective mass of those 11 suns, the total falls short, sometimes dramatically so. The orbits themselves are whispering that there is more mass present, a significant gravitational anchor lurking somewhere in the darkness, a ghost whose only signature is its persistent, unseen tug on the rest of the family. This is the Phantom Companion, a hypothetical 12th member whose nature is one of the most compelling mysteries in these already mysterious systems. The most likely candidate for this invisible presence is the remnant of a star that lived a violent, fleeting life and died long ago. Imagine one of the system's original 12 stars being born far more massive than its siblings. This stellar giant would have burned through its nuclear fuel in just a few million years, ending its life in a cataclysmic core collapse supernova. In that final titanic explosion, the star's outer layers were blasted into space, but its core collapsed under its own immense gravity. If the progenitor star was massive enough, this collapse would have resulted in the formation of a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Or if the original star was truly colossal, the collapse may have been unstoppable, resulting in a stellar mass black hole, a point in space where gravity is so intense that not even light can escape. In either case, the supernova explosion would have been asymmetrical, likely giving the newborn remnant a powerful kick velocity. Instead of being ejected entirely, this neutron star or black hole was somehow retained by the system's complex gravity, settling into a wide, dark orbit around the inner chaos, a stellar ghost haunting its former family. Detecting this phantom is a task that pushes observational astronomy to its absolute limits. A solitary neutron star that has cooled and is not actively feeding on a companion is virtually undetectable across interstellar distances. It emits no visible light and only a faint trickle of X-rays from its cooling surface. A stellar mass black hole, by its very nature, is completely black unless it is actively pulling gas from a neighboring star. So the search becomes indirect, a hunt for the subtle, telltale wobbles the phantom imparts on its visible neighbors. Astronomers look for stars whose paths exhibit a slight, yet persistent anomaly, a rhythmic drift that cannot be explained by the gravitational pull of the 11 other visible bodies. By meticulously mapping this wobble over years or even decades, they can triangulate the phantom's possible location and estimate its mass. It's a painstaking process of gravitational forensics, building a case against an invisible defendant based purely on its influence on the witnesses. The implications of confirming such a phantom are profound. Its presence would act as a living fossil, a direct record of a dramatic stellar death that occurred within the system billions of years ago. By studying its orbit, we could even work backwards to understand the mechanics of that ancient supernova, the kick it received, and how the system's gravity managed to corral such a runaway remnant. Furthermore, its sheer mass concentrated into a single dark point would act as a gravitational stabilizer for the entire system. This phantom could be the unseen conductor of the celestial orchestra, its steady, powerful pull helping to maintain the hierarchical order that prevents the entire family from flying apart, a dark king holding court from the shadows and ensuring the stability of its brilliant, chaotic realm. Yet to truly grasp the significance of these 12 star systems, we must trace them back to their violent and spectacular birthplaces, the dense, chaotic stellar nurseries where they first ignited. These cosmic maternity wards are already tumultuous environments, but the formation of a duodecuple system requires conditions that are nothing short of extreme. Their very existence points to a progenitor cloud of staggering proportions, a molecular cloud core so massive and so rich with turbulent energy that it could fragment not just into a handful of stars, but into a dozen all at once and in a configuration stable enough to endure. This isn't the gentle collapse that formed our solitary sun. This is a celestial Big Bang on a miniature scale, a ferocious burst of simultaneous creation where gravity's grasp was so overwhelming that it shattered a vast cloud into a complex hierarchical family right from the start. Think of a typical stellar nursery like the Orion Nebula. It's a bustling factory producing hundreds of stars, but most are single or in simple binaries. For a duodecuple system to emerge, the nursery must have been far denser, with the gas and dust packed so tightly that the distances between collapsing fragments were incredibly small. In such a crowded, high-stakes environment, the newborn stellar embryos would have begun their lives in a frantic gravitational scramble. Most would have been torn from their siblings in short order, cast out into the wider cluster by close encounters. The systems we see today, like TYC 7037-89-1, are the rare exceptions, the lottery winners, They are the surviving monarchs of a dynasty that managed to hold its territory against all odds, their complex architecture a direct testament to the unparalleled fertility and violence of their original home. This survival hinged on a critical, fleeting period just after their birth. For a brief window, while the system was still deeply embedded within its gaseous womb, the leftover material acted as a cosmic cushion. This shared envelope of gas created a powerful drag force, absorbing the excess kinetic energy from the most wildly orbiting stars and gently herding them into the stable, hierarchical groupings we observe today. Without this gaseous buffer, the system would have likely disintegrated before its stars even finished forming, its members scattered to become solitary wanderers in the galactic field. The fact that these systems held together means they formed quickly and found stability before this protective gas could be blown away by the intense radiation from their own hottest, youngest members. They are the product of a perfect, if violent, storm, a colossal cloud, rapid fragmentation, and a swift gravitational settlement that allowed a dozen suns to pledge allegiance to one another for billions of years. Even amidst the stellar pandemonium of a 12-star system, with its gravitational turmoil and lethal radiation, there emerges a stunning possibility for a sanctuary, a place where the relentless chaos outside is held at bay. This potential safe harbor isn't a planet orbiting a single star, but something far more intriguing, a massive exomoon orbiting a gas giant. Picture a Jupiter-like world that has, through sheer luck or gravitational cunning, found a stable orbit far enough from the system's turbulent core. This gas giant becomes a formidable fortress, and its large, icy moon, a world like a super-sized Europa or Titan, becomes a hidden oasis, perhaps the most life-friendly environment in the entire system. The key to this moon's survival lies in the multiple layers of protection offered by its host planet. First and foremost is the planetary magnetic field. A giant planet with a strong, dynamo-generated magnetosphere acts as a colossal shield. The deadly charged particles that flood the system, accelerated by tangled magnetic fields and stellar flares, are deflected around this protective bubble. The moon orbits safely within this magnetic cocoon, its surface spared from the constant, sterilizing particle rain that would otherwise scald it clean of any complex chemistry. Furthermore, the planet's immense gravity serves as a cosmic bodyguard. In a system where rogue planets and wayward asteroids are common due to gravitational perturbations, the gas giant's powerful pull acts as a gravitational shield. It captures or slingshots away many of the smaller, potentially impactor bodies that venture too close, drastically reducing the threat of catastrophic collisions for its orbiting moons. This creates a relatively peaceful neighborhood within the stellar war zone, but the true magic, the engine that could power life, comes from within the moon itself. This isn't a cold, dead rock, it's a world heated from the inside out. The source of this warmth is tidal heating. As the moon orbits its giant planet, the gravitational pull from the planet and possibly other nearby moons constantly flexes and kneads its interior. This friction generates immense heat, enough to maintain a vast, global subsurface ocean of liquid water beneath a thick, icy crust. This ocean could be dozens of miles deep, containing more liquid water than all of Earth's oceans combined, and it is entirely insulated from the apocalyptic conditions on the surface. In this eternal, dark abyss, the concept of a habitable zone becomes irrelevant. The dozen suns blazing in the sky above are completely unknown. Their light cannot penetrate the miles of ice that form the moon's protective shell. The energy for life here would not come from photosynthesis, but from chemosynthesis. On the ocean floor, around hydrothermal vents spewing mineral-rich, superheated water, entire ecosystems could potentially thrive. The base of the food chain would be microbes that convert chemical energy from the vents into organic matter, supporting a possible web of more complex organisms. For such life, the universe is not a sky of 12 suns, but the dark, warm water and the volcanic heat from below. The chaotic dance of the stars, the eclipses, the gravitational shocks, all of it is muffled into irrelevance. The Moon's biosphere would be utterly independent, a sealed, underground world whose rhythms are set by the geothermal pulse of its own core and the gravitational tug of its host planet, a serene and isolated existence in the heart of a cosmic storm. This exomoon haven represents a paradigm shift in our search for life in the most extreme environments. It teaches us that stability for biology isn't about a perfectly calm stellar neighborhood, but about finding the right kind of shelter. A large moon provides a stable gravitational anchor. A massive planet offers a protective magnetic and impact shield, and internal tidal heating supplies a reliable, long-term energy source completely decoupled from the violent and variable light of its many suns. In the grand, chaotic tapestry of a duodecuple system, these hidden oceanic worlds could be the ultimate refuges, the places where the flame of life, against all odds, finds a way to not just flicker, but to truly flourish in the darkness. We've seen how the tangled magnetic fields and colliding stellar winds weave a deadly web of energy, but this chaos also forges one of the most powerful natural engines in the universe, a cosmic ray accelerator operating on a scale that dwarfs anything humanity could ever build. Think of the entire volume of the duodecuple system not just as a space filled with stars, but as a colossal, naturally occurring particle collider. The fuel for this accelerator is the endless stream of charged particles, electrons and protons, that are constantly boiling off the surfaces of all 12 stars in their powerful stellar winds. In a calm system, these particles would gradually dissipate into the void, but here they are trapped within the system's intricate maze of magnetic fields, and that's where the real magic and the real terror begins. The acceleration process works through two primary, brutal mechanisms. The first involves the vast shock waves that ripple through the system from colliding stellar winds. When the hurricane force wind from a hot, massive star slams into the gentler breeze from a smaller companion, it creates a standing shock front, a wall of compressed, superheated gas and magnetic energy millions of miles across. A lone proton drifting through this region is like a speck of dust being caught in a tidal wave. The shock's immense magnetic field grabs the particle and hurls it forward, imparting a tremendous jolt of energy. The proton can cross this shock front not just once, but repeatedly, ricocheting back and forth as if trapped between two converging walls, gaining speed with each crossing until it is eventually ejected at a significant fraction of the speed of light. The second, even more efficient mechanism is magnetic reconnection. Remember the system-wide magnetic knot, the braided tangle of a dozen stellar fields. At points where these fields are forced together, they can suddenly snap and reorganize into a less tense configuration, like overstretched rubber bands breaking. This sudden snap unleashes a cataclysmic burst of energy, creating intense electric fields that can accelerate particles to near light speeds in an instant. The combined effect of these processes means the space within the system is perpetually flooded with a dense fog of high-energy particles, a bath of cosmic radiation so intense it would be instantly lethal to any known form of life. A spacecraft or planet within this environment would be subjected to a constant, silent rain of atomic bullets, shredding DNA, damaging electronics, and steadily eroding atmospheres. For biology, as we understand it, this isn't a challenging environment, it's an impossible one. Yet, this same lethal quality makes the duodecuple system a unique and invaluable laboratory for high-energy physics. The energies achieved in these natural processes can exceed those of our most powerful human-built accelerator, the Large Hadron Collider, by many orders of magnitude. By observing the gamma rays and other high-energy radiation emitted when these accelerated particles collide with stray atoms or light, astrophysicists can study the fundamental laws of physics under conditions that are impossible to recreate on Earth. This cosmic accelerator is conducting a continuous, galaxy-spanning experiment, probing the nature of matter and energy itself, and offering us a front-row seat to some of the most energetic processes in the cosmos. While the brilliant blue giants and dramatic stellar collisions command attention, the true, enduring heart of a duodecuple system may not be its most massive members, but its quietest and most numerous ones, the red dwarfs. These faint, cool stars, often weighing in at less than half the mass of our Sun, could easily make up the majority of the system's population. Their sheer numbers and extreme longevity introduce a gravitational anchor of profound stability amidst the larger, more chaotic interactions. Picture the system's core not as a frantic mosh pit, but as a slow, stately dance of ancient embers. Red dwarfs are the marathon runners of the stellar world. While a massive star might burn through its fuel in 10 million years, a typical red dwarf can fuse hydrogen for trillions of years, a lifespan so immense it far exceeds the current age of the universe. Their gravitational influence is gentle but persistent, and when many of them cluster together in the system's central regions, their collective pull can create a deep, steady gravitational well that acts as a kind of cosmic gyroscope. This dance of the dwarfs introduces a fascinating timescale to the system's evolution. The more massive stars live out their short, dramatic lives, exploding as supernova, merging, or shedding their outer layers to become white dwarfs. Through all this stellar fireworks, the red dwarfs remain largely unchanged, their slow nuclear furnaces barely flickering. As the violent, short-lived stars gradually disappear from the scene, the gravitational dynamics of the entire system begin to simplify. The primary sources of instability, the massive stars that drive collisions and ejections, are removed. What remains is a cleaner, more predictable gravitational field dominated by these long-lived, low-mass stars and the dark remnants of their departed siblings. The system's architecture simplifies from a chaotic 12-body problem to a more stable configuration governed by the collective, placid gravity of the dwarf population. Their slow, mutual orbits become the new clockwork of the system, a rhythm that will continue virtually unaltered for trillions of years to come. This gravitational steadfastness has a calming effect on the entire family. The presence of a large, stable mass of red dwarfs at the system's core helps to dampen the wilder orbital excursions of any remaining stars in wider orbits. It's akin to having a heavy, stable flywheel in a complex engine. It smooths out the vibrations and jerks, preventing smaller perturbations from escalating into system-wide chaos. A passing star from the outer reaches that might have previously caused a disruptive close encounter now finds its path gently shepherded and corrected by the steady, collective tug of the dwarf core. This slow motion dance ensures that even after the brilliant giants are gone and the white dwarfs have cooled to black, the duodecuple system retains its identity. It transitions from a vibrant, violent stellar metropolis into a quiet, ancient retirement community of faint, red suns, their patient dance ensuring the family stays together for eons longer than anyone might have thought possible. From a distance of hundreds of light years, the combined blaze of a dozen individual suns would merge into what seems to our telescopes to be a single, unremarkable point of light. This stellar point might exhibit a slight, rhythmic flicker, easily attributed to a lone, pulsating variable star or perhaps a simple eclipsing binary. The profound, intricate truth of a duodecuple family would be completely lost, its 12-part symphony condensed into a solitary, anonymous note in our star charts. This leads us to a humbling and revolutionary possibility. What we have long considered the fundamental building block of galaxies, the single, solitary star, may, in a staggering number of cases, be an illusion. Our stellar catalogues could be filled with cosmic con artists, simple points of light that are, in reality, dense stellar metropolises hiding in plain sight. The primary reason for this grand deception is the fundamental limitation of resolution. For most of astronomical history, our telescopes, even the powerful ones in orbit, simply could not distinguish two stars that are very close together in the sky. If two stars are separated by a distance equivalent to putting a pair of tennis balls on opposite sides of the United States and viewing them from Europe, their light blends seamlessly into one. This effect is compounded in a complex system where the stars are not just in tight pairs, but arranged in a hierarchy that places them at vastly different distances from us within the same patch of sky. The faint, wide-orbit companions are drowned out by the brilliant glare of the central pairs, their subtle light lost in the overwhelming photon stream of their brighter siblings. We see the combined output, the total luminosity, and we classify the object based on that blended signature, completely unaware of the intricate dance unfolding within. This means the star you might casually point out on a clear night could be a secret binary, a hidden quadruple, or perhaps even another as yet unidentified duodecuple system. The implications for stellar accounting are profound. If a significant percentage of what we classify as single stars are actually complex multiples, then we have drastically overestimated the number of stars in our galaxy while simultaneously underestimating the average number of planets per system. Imagine a star we thought was a solitary G-type star like our Sun. If it is actually a close binary, the dynamics of any surrounding planetary system are completely different. The stable, circular orbits we associate with habitability are far less likely. Our entire statistical understanding of the galaxy's architecture, from stellar populations to planetary formation, requires a fundamental revision if the single star is not the default, but merely the simplest face a more complex system can present. Unmasking these stellar impersonators requires moving beyond simple photography to the detective work of indirect methods. The telltale wobble detected by radial velocity measurements is one of the most powerful tools. A star that shifts its light rhythmically from blue to red is being tugged by an unseen companion, but in the case of a complex system, that wobble isn't a clean, sinusoidal wave. It's a messy, multi-layered signal, a superposition of several different orbital periods that requires sophisticated computer modeling to untangle. Similarly, the transit method used by planet-hunting missions like Kepler and TESS can reveal these hidden systems. The chaotic, multi-dipped light curve of TYC 7037-891 was the key that unlocked its 12-star nature. As we reanalyze old data from these missions with new algorithms designed to spot these complex patterns, we are likely to find that many stars previously flagged as having unexplained noise or peculiar variability are in fact complex multiples whose story we are only now learning to read. This realization forces us to look at the entire cosmos with new eyes. The quiet, orderly galaxy we thought we knew is, in truth, far more sociable, dynamic, and densely packed. The serene backdrop of the Milky Way, a tapestry of countless individual diamond-like points, is an illusion. In reality, it is a teeming, bustling network of stellar families, from simple pairs to elaborate dozen star clans, their complex gravitational bonds weaving a hidden architecture throughout the spiral arms. The very concept of a star's identity becomes fluid. A point of light is not a thing, but a relationship, a community whose true nature remains one of the universe's most brilliantly kept secrets, waiting for us to develop the tools and the patience to listen to its multi-voiced song. In a system as crowded and gravitationally restless as this, the debris fields left over from planet formation would not be the serene, orderly rings we picture in our own solar system. Instead of the relatively stable asteroid belt between Mars and Jupiter or the distant, placid Kuiper belt, a duodecuple system would host a region of pure chaos, a cosmic pinball machine where the pegs are the gravitational fields of a dozen stars and the balls are trillions of icy and rocky planetesimals. The forces at play here are relentless. With so many massive bodies constantly on the move, their combined gravity creates a shifting, turbulent sea of perturbations. An asteroid orbiting peacefully around one star can find its path suddenly and violently altered by the passing tug of a different stellar pair millions of miles away. These aren't gentle nudges, they are sharp, unpredictable kicks that send objects careening on new, often disastrous trajectories. The primary game being played in this celestial arcade is gravitational scattering. An object in the equivalent of an asteroid belt might be in a stable orbit for thousands of years, a tiny world minding its own business. But then, the complex dance of the stars brings a massive gravitational perturber close by. The path of the asteroid is now deflected, its orbital energy changed. In countless simulations, these interactions have one of three dramatic outcomes. The first is a collision course. The altered trajectory sends the asteroid plunging inward toward the inner sanctum of the system. It becomes a projectile aimed at the terrestrial planets or even the stars themselves, a potential agent of planetary sterilization or a source of new material for a stellar atmosphere. The second outcome is even more final: ejection. The gravitational slingshot can impart so much energy that the asteroid achieves escape velocity, flinging it out of the system entirely to become a lone, dark wanderer in interstellar space. The third, and perhaps most bizarre, fate is capture. An asteroid originally belonging to one star can be snatched away by the gravity of another, becoming a permanent member of a different stellar subgroup within the same extended family. This constant gravitational jostling means the density of objects in these belts would be far lower than in our solar system. The pinball machine is brutally efficient at clearing its own table. Over millions of years, a vast majority of the original planetesimals are ejected, leaving behind a much sparser population. However, the ones that remain are the survivors of a relentless gravitational selection process. They are the objects that have, through sheer luck or orbital resonance, found stable niches, paths that are somehow protected from the worst of the perturbations, like a single pinball finding a groove where it can roll safely without hitting a bumper. These surviving asteroids and comets would be the veterans, their orbits a testament to a long and violent history. The consequences of this non-stop pinball game for any inner planets are dire. The rate of impacts would be orders of magnitude higher than anything experienced in our solar system's history, even during the late heavy bombardment. A world in the system's tentative habitable zone would be under constant siege. The sky would frequently be streaked with the brilliant flashes of incoming asteroids and comets, each one a potential extinction-level event. This relentless bombardment would make it incredibly difficult for life to gain a foothold, as any nascent biosphere would be repeatedly reset by global firestorms and impact winters. The planetary surfaces would be a cratered wasteland, geologically young and constantly churned, their landscapes a stark record of the perpetual violence raining down from the chaotic belts beyond. In such an environment, the very concept of a stable, long-term climate is shattered, replaced by a history of catastrophic upheavals dictated by the gravitational whims of a dozen suns. But within this gravitational whirlwind, the stars themselves are not isolated actors. They are intimate partners in a constant physical exchange that rewrites their very nature in a process of stellar metamorphosis. In the calm of our own galactic neighborhood, a star's fate is largely sealed at birth. Its mass dictates its temperature, its color, and the entire timeline of its life, from hydrogen-burning maturity to its final death. But place that same star into a tight binary pair within a duodecuple system, and its destiny is no longer its own. It becomes part of a celestial symbiosis or a parasitic relationship that can fundamentally alter its structure and lifespan in ways that defy the standard stellar models. The most dramatic mechanism for this change is mass transfer, a cosmic transfusion of stellar material that can rejuvenate a dying star or create a monstrous hybrid. Picture a common pairing in such a system, a bloated red giant and a compact, dense white dwarf orbiting perilously close to one another. The red giant has expanded so much that its outer layers are only loosely bound by gravity, existing in a region of space known as the Roche lobe. This is the star's gravitational domain, the area where its own pull is stronger than that of its companion. But as the red giant swells further, its material can spill over the boundary of this lobe like water overflowing a cup. Once it crosses this gravitational watershed, the matter falls under the dominant influence of the white dwarf's intense gravity. It doesn't fall directly onto the dead star. Instead, it spirals in, forming a brilliant, hot disk of accretion around it, a temporary reservoir of stolen life. This transfer of mass has transformative and often violently contradictory consequences for both stars. For the donor star, the red giant, it's a process of rapid and unnatural weight loss. It is being systematically stripped of its hydrogen-rich outer envelope. If this process continues, the red giant can be peeled down to its bare, hot helium core long before it would have naturally ended its life, creating a premature subdwarf. For the recipient white dwarf, this new material is both a gift and a curse. The fresh hydrogen piling up on its surface creates immense pressure and heat. Eventually, this layer can ignite in a runaway thermonuclear fusion reaction, causing a nova explosion that blasts the accumulated material back into space in a brilliant flash. This doesn't destroy the white dwarf, but it does reset the process, allowing it to begin feeding again. If the transfer rate is particularly high, however, the white dwarf can avoid these nova outbursts and instead steadily grow in mass. If it approaches the Chandrasekhar limit of about 1.4 solar masses, the entire carbon-oxygen core can detonate in a Type Ia supernova, a titanic explosion that utterly annihilates the star. The very existence of these supernovae in such systems is direct evidence of this transformative mass transfer, a stellar death triggered by a companion's generosity. Beyond the outright theft of mass, the constant, intimate gravitational embrace between stars exerts a more subtle but equally powerful force: tidal heating. We often think of tides as something that affects oceans, but on a stellar scale, the effect is far more profound. The gravitational pull from a close companion doesn't just raise a bulge on a star, it actively kneads its interior like dough. As the stars orbit, the direction of this gravitational pull changes, constantly flexing and distorting their shapes. This internal friction generates immense heat deep within the stellar core, supplementing the energy produced by nuclear fusion. For a low-mass red dwarf, this extra tidal heating can be transformative. In isolation, such a star would have a relatively cool interior and a placid, stable existence. But with a close, massive partner, tidal heating can significantly raise its core temperature, causing it to burn its hydrogen fuel more efficiently and shine more brightly than a star of its mass has any right to. It's as if the star is being kept artificially young and vigorous by the constant gravitational workout imposed by its neighbor. This internal churning also has a dramatic effect on a star's magnetic activity. The differential rotation between the tidally distorted outer layers and the more rigidly rotating core acts as a powerful dynamo, amplifying the star's magnetic field to extraordinary intensities. This leads to a constant storm of stellar activity, monstrous flares, and coronal mass ejections that erupt from its surface, bathing the entire local environment in lethal radiation. A star that should have been a quiet, steady beacon becomes an unpredictable flare star, its personality fundamentally altered by the relentless gravitational massage from its companion. This means that in a duodecuple system, you cannot judge a star by its mass alone. Its behavior, its temperature, and even its internal structure are shaped by the company it keeps, turning the standard Hertzsprung-Russell diagram, which classifies stars by luminosity and temperature, into a chaotic map of stellar outliers and impossibilities. Perhaps the most extreme form of stellar metamorphosis occurs not from a steady drip of material, but from a single crushing event, gravitational compression during a close stellar passage. In the crowded core of the system, stars are forever weaving around one another, and sometimes their paths bring them alarmingly close. During such an encounter, the gravitational field of a passing star can act like an invisible vise, violently compressing its neighbor. For a star that is already in a vulnerable state, such as a red giant with a degenerate helium core that is just on the verge of igniting, this sudden external pressure can be the final push it needs. The compression raises the core's temperature and density past the critical point for helium fusion to begin. But this ignition isn't the gentle start of a new phase of life. It's a catastrophic thermal pulse known as a helium flash. The star doesn't smoothly transition. It convulses, violently expelling its outer layers in a series of shocks that can completely reshape its appearance in a cosmic instant. This process of forced evolution can create bizarre stellar objects that have no counterpart in isolated space. A star could be prematurely stripped of its envelope to become a hot subdwarf, or have its core evolution artificially accelerated, causing it to skip entire chapters of its life story. The stellar population within a duodecuple system is therefore not a collection of individuals following separate, predictable paths. It is an interconnected web, a society of suns whose lives are deeply entangled. A star's size, temperature, lifespan, and ultimate fate are not predetermined by its birth mass, but are continuously negotiated through a lifetime of gravitational interactions, mass exchanges, and tidal influences. In this environment, a star is not a solitary entity, but a fluid character in an ongoing drama, its identity forged and remade by the constant physical intimacy of its celestial family. And within this storm of light and energy, we find one of the most elegant methods for mapping this celestial labyrinth, the echoes of light. Imagine for a moment the sheer, mind-bending scale of such a system. A brilliant, unexpected flash erupts, perhaps a superflare from a magnetically tortured star, or the final, cataclysmic detonation of a white dwarf supernova. For a single, dazzling instant, a torrent of photons, a near infinite number of light particles, explodes outward in an expanding sphere, traveling at the ultimate speed limit of the universe. Most of this light travels unimpeded, racing directly away into the void, but a tiny fraction of it is destined for a more interesting journey. These photons slam into the countless motes of dust that permeate the system, the same dust that forms the raw material for planets and the enigmatic structures we discussed earlier. They also strike the intensely reflective, highly ionized surfaces of the stellar winds blowing from other stars. Upon impact, they don't just vanish, they scatter, reflecting off these surfaces and being sent off in new, unpredictable directions. What reaches a distant telescope, perhaps years or even decades after the initial flash, is not just the direct light from the event itself. It is followed, like a cosmic applause arriving late from the back of a vast hall, by a series of faint, repeated glows, the light echoes. Each echo is a ghost, a delayed signal that has taken a longer, more scenic route through the system. The path it took is the key. An echo that arrives a year after the main flash has traveled an extra light year in total distance. By meticulously measuring the time delay and the precise brightness of each echo, astronomers can perform a feat that seems like pure magic. They can triangulate the three-dimensional positions of the dust clouds and stellar surfaces that cause the reflection. It's as if the initial flash of light is a sonar ping in a dark ocean, and the returning echoes are painting a detailed topographical map of the entire submerged landscape. This turns a single, fleeting stellar explosion into a long-term mapping mission. A supernova doesn't just vanish after its primary flash fades. It continues to illuminate its surroundings for years, its light echoing off structures progressively farther and farther away. In a duodecuple system, the data this provides is priceless. An echo detected from one particular direction might reveal the presence and precise distance of a previously unknown dust shell surrounding one of the wider orbit binary pairs. Another, fainter echo from a different part of the sky could trace the complex, warped surface of a colliding wind region between two other stars. Over time, a complete three-dimensional blueprint of the system's inner architecture begins to emerge from the echoes, revealing cavities carved by stellar winds, dense rings of planet-forming material, and the vast, empty gulfs between the stellar subgroups. This is not a static map either. Because the stars are in constant motion, the echoes from subsequent flares will reflect off these structures from slightly different angles, allowing scientists to not only map the system's shape, but also to measure the velocities and directions of its moving parts, creating a dynamic, four-dimensional model of the entire stellar family in motion. And yet, this gravitational storm offers more than just chaos and destruction. It presents a fleeting, natural laboratory for probing the very fabric of reality. The titanic forces at play in a duodecuple system, particularly during a close stellar encounter, stress spacetime in ways that are almost unimaginable, creating conditions where the two great pillars of modern physics, Einstein's general relativity and quantum mechanics, are forced to confront one another. To understand why this is so significant, consider the fundamental disconnect in our current understanding of the cosmos. General relativity gives us a breathtakingly accurate picture of the universe on large scales, describing gravity as the curvature of spacetime by mass and energy. It perfectly predicts the orbits of planets, the bending of light, and the slow dance of binary pulsars. Quantum mechanics, on the other hand, rules the infinitesimally small world of atoms and particles, a realm of probability, uncertainty, and weirdness. Both theories are spectacularly successful in their own domains, but they are fundamentally incompatible. They speak different mathematical languages and make contradictory claims about the nature of reality, especially when gravity becomes incredibly strong and the scale becomes incredibly small, such as at the center of a black hole or at the moment of the Big Bang. Unifying them into a single theory of quantum gravity is arguably the greatest unsolved problem in all of physics. This is where the violent intimacy of a 12-star system becomes a potential testing ground. During a close passage between two stars, especially if one is an ultra-dense neutron star, the gravitational fields involved are not just strong, they are dynamic and changing with ferocious speed. The curvature of spacetime isn't a static bowl, it's a churning, turbulent whirlpool. According to general relativity, this wildly fluctuating geometry should, in theory, produce ripples in spacetime itself, gravitational waves. We've detected these waves from merging black holes and neutron stars, but the signals from a close stellar encounter in a system this complex would be a continuous cacophony of overlapping frequencies, a gravitational background hum of unparalleled richness. But the real magic might occur in the quantum realm. Many theoretical physicists propose that on the tiniest possible scale, at the so-called Planck length, spacetime itself might not be smooth and continuous as general relativity assumes. Instead, it could be foamy and discrete, made of tiny, quantized atoms of space and time. In most of the universe, this quantum foam is completely undetectable. Its grain is so fine we could never hope to perceive it. But when spacetime is being violently stretched and compressed by the gravitational tides of two passing stars, that fine-grained, foamy structure might leave a tiny, subtle imprint on the gravitational waves propagating through it. It would be like trying to detect the microscopic texture of a pond's surface by observing how ripples travel across it. In calm water, you see only the ripple, but in a violently churning sea, the fundamental properties of the water itself might influence the wave. One potential signature of this quantum grain could be a subtle dispersion of gravitational waves. In a perfectly smooth spacetime, as described by classical general relativity, gravitational waves of all frequencies should travel at the same speed, the speed of light. But if spacetime has a foamy quantum structure, very high-frequency gravitational waves might interact with that foam, slowing down ever so slightly compared to their lower-frequency counterparts. A close stellar encounter, especially one involving a neutron star, could generate a broad spectrum of these waves. By the time this complex signal traveled across thousands of light years to our detectors, like LISA, the future space-based gravitational wave observatory, the highest frequency components might arrive an infinitesimal fraction of a second later than predicted by pure general relativity. That minuscule delay, that tiny scar on the signal, would be the first experimental evidence that spacetime itself is quantized, a discovery that would fundamentally rewrite our understanding of the universe. Furthermore, the sheer energy density in the region between two closely passing stars could be so immense that it might momentarily allow for the spontaneous creation of virtual particles in ways that are normally forbidden. In the quantum vacuum, particle-antiparticle pairs are constantly flickering in and out of existence. Normally, they annihilate each other almost instantly. But in an intensely curved spacetime, a phenomenon known as the Schwinger effect could allow these virtual particles to be ripped apart by the gravitational field itself, becoming real and potentially detectable. This would be a direct demonstration of gravity acting on the quantum scale, a tangible link between the two worlds. Of course, observing these effects is a monumental challenge that pushes the limits of both theory and technology. The signals would be incredibly faint, buried in the noise of the chaotic system and the instrumental limits of our detectors. It would require modeling the encounter with a precision we do not yet possess, accounting for the exact masses, shapes, and magnetic fields of the stars involved. But the mere possibility is what electrifies physicists. A duodecuple star system offers a natural, if terrifying, particle accelerator and a space-time stress testing facility of a scale we could never hope to build. By carefully monitoring the gravitational waves and electromagnetic radiation from such a system over decades or even centuries, we might be lucky enough to witness a stellar close call of just the right kind. In that brief cosmic moment, as two stellar titans swing past each other, warping the void around them into a pretzel of distorted geometry, they might inadvertently perform the ultimate physics experiment, revealing secrets about the quantum structure of reality that have been hidden since the birth of the universe. Tucked away in the faint, smeared lines of a star's spectrum is its entire life story, a chemical autobiography written in the language of atomic absorption. In a solitary star like our Sun, this story is relatively straightforward, a chronicle of its initial composition from the primordial birth cloud. But in a duodecuple system where stars are born together and then spend billions of years in intimate, often violent proximity, these chemical fingerprints become something far more profound. A collection of celestial case files for a team of cosmic archaeologists. By decoding the unique elemental abundances in each of the 12 suns, scientists can perform a stellar autopsy, piecing together a history of cannibalism, catastrophic explosions, and shared pollution that has shaped the family over eons. It's a detective story written in starlight where the clues are atoms themselves. The foundational principle of this cosmic sleuthing is nucleosynthesis, the process by which stars forge new elements in their cores. Different types of stars create different sets of elements. A slow-burning, low-mass red dwarf will primarily produce helium from hydrogen over its immense lifespan. A star like our Sun will eventually create carbon and oxygen, but the truly heavy elements, things like silicon, iron, gold, and uranium, are forged in the most extreme conditions, the furious hearts of massive stars and their subsequent supernova explosions. In a placid system, these elements are mixed uniformly throughout the birth cloud, so all sibling stars start with nearly identical chemical signatures. In a duodecuple system, however, that uniform starting point is quickly obliterated by the very events that define its chaotic nature. One of the most telling pieces of evidence a cosmic archaeologist looks for is a signature of stellar vampirism. Imagine analyzing the spectrum of a star that, by all other accounts, appears to be a normal main sequence star. Yet, its atmosphere shows a surprising overabundance of elements like carbon and nitrogen, along with the distinct isotopic signature of a process called slow neutron capture, or the S process. This is the hallmark of a star that has been chemically polluted, not by its own internal processes, but by a companion. The scenario unfolds with a binary pair where one star has already evolved into a red giant and begun S-process nucleosynthesis in its deep interior. If its outer, chemically enriched layers are then stripped away and transferred onto the surface of its companion star, the recipient becomes a living record of this theft. The receiving star's outer atmosphere is now contaminated with the ashes from its partner's nuclear furnace. We see a star that looks young and normal, but its chemistry screams that it has gorged itself on the processed remains of its dying sibling. This is direct chemical proof of mass transfer, an event frozen in the stellar data. Even more dramatic is the chemical fallout from a supernova. When a massive star ends its life in a core collapse supernova, it blasts newly forged heavy elements like oxygen, magnesium, and most tellingly, radioactive isotopes like aluminum-26 out into its surroundings at nearly the speed of light. In a densely packed stellar system, this ejector doesn't just drift off into empty space. It can directly slam into the atmospheres of nearby sibling stars. Astronomers might observe a star whose spectrum is anomalously rich in these specific elements, a clear sign that it was, quite literally, sprayed with the shrapnel from a nearby stellar explosion millions of years ago. The presence of certain elements or their specific ratios can even act as a timer. By measuring the decay products of short-lived radioactive isotopes, scientists can estimate when that pollution event occurred, adding a temporal dimension to the archaeological record and dating the system's most violent historical chapters. The aftermath of a stellar merger leaves its own distinct chemical scar. When two stars collide and merge, as they so often do in these chaotic environments, their internal layers are violently stirred together. The result is a new star with a thoroughly mixed and homogenized composition. If one of the progenitor stars had already begun to fuse helium into carbon in its core, that carbon will be dredged up and spread throughout the entire new star. The resulting object, often observed as a blue straggler, will have a surface abundance of carbon that is completely out of line with its apparent mass and age. It's a chemical paradox, a star that looks young but contains the nuclear waste products of an older star, the indelible signature of a violent union that reset its evolutionary clock. By conducting this chemical census across all 12 members of the system, a breathtakingly detailed family history emerges. The stars that show pristine, unaltered compositions are likely the ones that have spent their lives in wide, stable orbits, untouched by the inner turmoil. Those with enriched atmospheres are the ones that have been actively feeding on companions or were bathed in supernova debris. The ones with the most bizarre, mixed-up compositions are the survivors of mergers. Each star becomes a chapter in a shared biography, and by reading them all together, astronomers can reconstruct a timeline of the system's most dramatic events. Which star died first in a supernova, which binary pair engaged in mass transfer, and which two stars merged to create a brilliant blue straggler. This isn't just studying stars as they are now. It's a form of celestial forensics, using the elemental clues they carry to piece together the epic, violent, and interconnected saga of their lives. So this brings us to a perspective shift so profound it changes our very understanding of what a star system is. We must learn to see this magnificent 12-star architecture not as a permanent celestial cathedral, but as a glittering, transient city. The intricate dance we observe today is merely a single, frozen frame in a movie that spans billions of years. The gravitational bonds that hold this family together are constantly being tested and rewritten by the very chaos they create. Over timescales that dwarf human history, the stellar metropolis we call a duodecuple system will undergo a dramatic and inevitable urban renewal, its skyline forever altered by evictions, mergers, and catastrophic redevelopments. The city of stars is alive, and its population is in constant flux. The primary engine of this change is the slow, relentless drain of gravitational energy. Every close encounter between stars, every intricate three-body interaction, acts like a subtle transaction in a cosmic bank account. The currency is kinetic energy, and the system is slowly spending it. When two stars make a close pass, the least massive one often gains energy, being pushed into a wider, more unstable orbit, while the other sinks deeper into the gravitational well. Over millions of such encounters, this statistical process guarantees that some stars will eventually accumulate enough energy to achieve escape velocity. They are, in effect, evicted from the city. A star that has been a stable resident for 1 billion years can suddenly find itself cast out, becoming a runaway, destined to wander the galactic hinterlands alone. This means the 12-star system we catalog today might, in 10 million years, be an 11-star system, and then a 10-star system, its population slowly dwindling as its most gravitationally footloose members are voted off the island by their siblings. Alongside these quiet evictions, the city is also shaped by sudden, violent construction project stellar mergers. In the densely packed downtown core, where the tightest binaries and quadruple systems whirl, orbital paths can and do cross. A close gravitational encounter between two binary pairs can perturb their orbits just enough to turn a stable dance into a death spiral. When two stars finally merge, it's not a gentle blending but a catastrophic restructuring. The resulting new star, a blue straggler, is like a gleaming new skyscraper built on the site of two demolished older buildings. It is brighter, hotter, and more massive, instantly changing the gravitational and radiative landscape of its entire neighborhood. Its increased mass exerts a stronger pull on its neighbors, potentially destabilizing other delicate orbital arrangements and triggering a cascade of further dynamical changes. A single merger can thus rewrite the city's zoning laws for eons to come. And then there are the sudden, neighborhood-clearing events, the supernova. The death of a massive star is the ultimate urban renewal project, one that doesn't just alter the skyline but fundamentally changes the city's gravity. When a star 20 times the mass of our Sun explodes, it instantly blasts over 90% of its mass into interstellar space. The gravitational anchor that this star provided simply vanishes. Imagine a city where one of the largest, heaviest buildings suddenly dematerializes. The infrastructure that depended on its weight and presence is thrown into chaos. The star's binary partner, if it survives the blast, is now untethered, sent careening on a new, unpredictable path like a wrecking ball through the city streets. The orbits of every other star that felt its pull are now slightly different, their rhythmic paths now stuttering and shifting as they seek a new equilibrium around a suddenly lighter core. A supernova doesn't just remove one resident, it forces every other citizen to find a new place to live in the gravitational metropolis. So, the majestic configuration we see through our telescopes, this 12-star hierarchy that seems so impossibly complex, is nothing more than a temporary consensus. It is a fragile, hard-won truce in a perpetual gravitational war. The city is always evolving, its structure fluid over the deep time of the galaxy. The Duodecuple system is not a finished sculpture, but a work in progress, a dynamic and ever-changing collective whose story is one of constant construction, demolition, and rebirth, a testament to the universe's relentless drive toward complexity and its inevitable return to simplicity. But beyond the light and the radiation, the very fabric of the cosmos is being rhythmically stretched and squeezed by this stellar family. Every orbit, every close pass, every sudden acceleration sends a tremor through space-time itself, a ripple that propagates outward at the speed of light. In a simple binary system, these gravitational waves are like a single, pure note, a steady hum, whose frequency and amplitude reveal the masses and separation of the two stars. But in a duodecuple system, the output is not a solitary note, but a roaring, overlapping chorus. Each of the dozen stars, along with every tight binary pair and every larger stellar subgroup, is a separate instrument in this cosmic orchestra, all playing their own gravitational melodies simultaneously. The innermost eclipsing binaries contribute frantic, high-frequency chirps as they whip around each other every few days. The wider orbits of the quadruple and sextuple systems produce deeper, more resonant tones like the long, low strings of a cello. And the slow, stately dance of the outermost stellar pairs adds a foundational hum, a bass note so deep it might take centuries to complete a single cycle. This gravitational wave chorus is a cacophony of immense power, a direct result of Einstein's theory of general relativity in action. The theory tells us that any mass undergoing acceleration will produce these ripples, and the amount of energy carried away is staggering when you have 12 massive suns constantly changing each other's trajectories. The sheer violence of their gravitational interactions, the close encounters that nearly lead to collisions, the sudden slingshot maneuvers that eject a star, the chaotic three-body interactions within the core, all of these events inject sharp, transient bursts of energy into the gravitational wave spectrum. These aren't the clean, predictable signals from merging black holes. This is a continuous, turbulent roar of spacetime itself, a sonic representation of the system's inherent orbital chaos. If our ears were tuned to the frequency of spacetime vibrations, the sound coming from this system would be an overwhelming, dissonant symphony, beautiful and terrifying in its complexity. For now, this chorus remains just below the threshold of our detection. Our current gravitational wave observatories, like LIGO and Virgo, are exquisitely tuned to listen for the high-frequency, cataclysmic crashes of stellar mass black holes and neutron stars. The lower frequency, continuous hum of a complex multiple star system is currently beyond their reach, but the future of astronomy holds the key to unlocking this song. The planned space-based observatory LISA, the Laser Interferometer Space Antenna, is being designed specifically to listen to this lower register of the gravitational wave spectrum. Instead of detectors here on Earth, LISA will consist of 3 spacecraft flying in a vast triangular formation millions of miles on a side connected by lasers. Free from the seismic noise of our planet, this incredible instrument will be able to perceive the subtle stretching of spacetime caused by the kind of persistent, multi-source signals a duodecuple system produces. When LISA finally begins its mission, listening to a system like this will be like tuning into a radio station broadcasting the universe's deepest secrets. Untangling the individual voices within the chorus will be a monumental computational challenge, a feat of signal processing that will require building a fantastically detailed model of the entire system's architecture and dynamics. But the payoff will be a new way of seeing, or rather hearing, the cosmos. Gravitational waves are not blocked by dust or gas. They pass straight through the vast clouds that can obscure our optical and radio views. By listening to this spacetime chorus, we could map the orbits of these stars with a precision that light-based astronomy could never achieve. We could directly measure the masses of the stars, confirm the existence of any hidden black hole or neutron star companions, and even witness in real time the subtle orbital decay and instabilities that foretell the system's future evolution. The gravitational wave chorus is the system's true voice, a direct broadcast of its gravitational heart, and one day soon we will have the technology to finally lean in and listen. This notion of a shifting habitable zone leads us to one of the most haunting planetary fates imaginable, the existence of shadow worlds. These are not planets in the simple night of a rotating world, but entire globes plunged into profound, multi-year darkness, not by their own spin, but by the complex celestial choreography of their many suns. To understand this, picture a planet in a wide P-type orbit around the system's central core of stars. Its year is defined by this long loop around the gravitational center of the entire family. For a portion of this orbit, its path carries it into a position where, from its perspective, the primary suns are clustered together, blazing in the sky and bathing it in intense, multi-directional light. This is its summer, a period of potentially unbearable heat, but as it continues its journey, it eventually swings around to the opposite side of its orbit. Here, the geometry of the heavens shifts dramatically. The brilliant central stars are now all clustered behind a single, more distant star, or perhaps even behind a duo of stars that are themselves eclipsing each other. From the planet's surface, this creates a perfect alignment, a multi-layered stellar eclipse of cosmic proportions. The result isn't a brief period of twilight like a solar eclipse on Earth. This is a season of darkness. The planet enters the combined shadow of 2, 3, or even more stars, a vast cone of umbral shadow that stretches millions of miles into space. As it traverses this shadow, the world is plunged into a deep winter that has nothing to do with axial tilt and everything to do with a simple, cruel lack of light. The primary sources of heat and light are completely blocked. The sky would still contain other, more distant suns, but they would be mere pinpricks, like especially bright stars in our night sky, providing negligible warmth. The temperature would plummet not by dozens of degrees, but by hundreds. On an Earth-like world, the oceans would begin to freeze, not just at the poles, but from the equator outward. The atmosphere itself would start to collapse. Gases like nitrogen, oxygen, and carbon dioxide would condense, first forming a dense global fog and then falling as snow, creating a landscape of frozen air lying atop a global glacier of ice. The entire world would enter a state of cryogenic suspension, a deep freeze so complete that the very air you breathe would become a solid blanket on the ground. The thaw, when it finally comes, is not a gentle spring. After years or even decades in this stellar shadow, the planet's orbit inevitably carries it back into the light. The end of the eclipse would be a violent global event. The first primary star to reappear would flood the frozen landscape with intense radiation. The surface ice would begin to sublimate, turning directly from solid to gas without a liquid phase, but the process would be chaotic and catastrophic. The frozen atmosphere on the ground would rapidly vaporize, creating hurricane-force winds as the pressure skyrocketed. The planet would be engulfed in a global storm of its own reanimating air. Flash melting and sublimation could cause colossal flooding and mudslides on a continental scale. The climate would swing from a deep freeze to a superheated greenhouse effect in a geological instant, as the thick, newly gaseous atmosphere traps the incoming heat from the now visible suns. A world that was a frozen, silent ball of ice could be transformed into a steaming, tempestuous cauldron in a matter of a few short years. For any potential life, this cycle presents an unimaginable challenge. Evolution would have to find a way to cope with a complete reset of the biosphere every single orbit. Life wouldn't just hibernate, it would need to survive a process that regularly turns the entire planet into a different world. The only conceivable niches would be deep underground or at the very bottom of oceans thick enough to not freeze solid, where geothermal heat could provide a constant minimal refuge. On the surface, any complex ecosystems would be wiped out each cycle, their fossils ground to dust by the advancing glaciers and then scoured away by the violent floods of the thaw. A shadow world is a place of eternal, rhythmic cataclysm, a testament to the fact that in a universe of 12 suns, even something as fundamental as a season can become an agent of planetary apocalypse. Yet even within this gravitational storm, there are moments of breathtaking precision, fleeting instances where the cosmos seems to take a perfectly synchronized breath. This is the phenomenon of tidal locking on a grand, systemic scale. where the relentless gravitational pull between close stellar neighbors forces their rotation into a cosmic waltz. Over millions of years, the same tidal forces that stretch stars into ovals act as a braking mechanism, gradually slowing a star's spin until its rotation period becomes perfectly matched to its orbital period around a companion. The result is a state of eternal facing, much like our moon always shows the same face to Earth. But in a duodecuple system, this effect isn't limited to a single pair. It can create a temporary, intricate network of locked relationships, a web of celestial synchronicity where multiple stars become gravitationally choreographed. Imagine one of the innermost binary pairs, two stars locked in a frantic, close orbit. Over eons, they have tidally evolved to a state where each star perpetually shows the same hemisphere to its partner. They are a fixed, whirling duo, one side of each star forever bathed in the searing light of the other, while the opposite hemisphere stares eternally into the cold void. This creates a world of permanent extremes. The day side of each star becomes a superheated furnace, its atmosphere churning with violent storms fueled by the intense, unending irradiation. The night side, meanwhile, cools to a much lower temperature, creating a colossal temperature gradient that drives supersonic winds around the star's terminator line, the border between eternal day and endless night. These stars are no longer uniform spheres, they are gravitational sculptures, their very weather patterns dictated by this forced, intimate embrace. But the true spectacle begins when you scale this phenomenon up. In the system's core, you might find that two such tidally locked binaries are themselves orbiting each other. For a brief window of cosmic time, the orbital periods of these two pairs can fall into a simple, resonant ratio with their own internal spin-orbit locks. Picture this binary pair completes exactly 2 orbits around the system's barycenter for every 3 orbits completed by binary pair B. At the same time, the individual stars within each pair maintain their perfect one-to-one rotation orbit sync. This creates a fleeting, multi-layered harmony, a celestial clock where 4 separate timing mechanisms are all ticking in a precise, predictable rhythm. For any planets nestled within this temporary gravitational haven, it would be a golden age of stability. The complex, overlapping cycles of light and heat from the 4 suns would settle into a repeating, predictable pattern, offering a rare period of climatic regularity in an otherwise chaotic existence. This synchronization acts as a powerful stabilizing force for that entire pocket of the system. The rhythmic gravitational tugs between the locked stars prevent wild orbital excursions, creating a cooperative dance that protects them from perturbing influences, even from the other 8 stars in the wider system. It's a natural feedback loop of harmony. The resonance begets stability, which in turn reinforces the resonance. This gravitational scaffolding acts like a flywheel in a great engine, smoothing out the violent jerks and vibrations that would otherwise tear the stellar family apart. For a few thousand years, a mere blink in cosmic terms, this small corner of the maelstrom finds a fragile, beautiful order. However, this cosmic harmony is inherently transient, perpetually threatened by the very nature of the system it briefly governs. The gravitational influence of the other, non-resonant stars acts like a constant, subtle background noise, a dissonant hum that eventually unravels the perfect tune. Their distant tugs gradually inject tiny amounts of energy into the resonant configuration, perturbing the delicate balance. Over centuries or millennia, these minuscule nudges accumulate like grains of sand piling up on one side of a perfectly balanced scale. The precise orbital ratios begin to drift imperceptibly. A period that was once exactly 2/3 of another becomes 2.001/3. The perfect clockwork begins to develop an almost invisible wobble. The breakdown is not a gradual unwinding, but a sudden and complete collapse. The resonant state is a precarious equilibrium, and once it's perturbed beyond a critical threshold, it shatters. The synchronized dance disintegrates into chaos. the gravitational scaffolding vanishes and the stars revert to their true, independent natures, their orbits beginning to meander and drift once more. The temporary era of harmony is over, and the system returns to its default state of glorious, unpredictable turbulence. This cycle of temporary order emerging from and then dissolving back into chaos is a fundamental characteristic of complex gravitational systems, a poignant reminder that even in the most extreme environments, the universe has a fleeting appreciation for a perfect, intricate rhythm. Attempting to predict the weather in such a system would be a task that defies our very understanding of prediction. It wouldn't be like forecasting a hurricane on Earth, where we track a single, cohesive system across an ocean. This would be like trying to predict the precise pattern of splashes in a swimming pool, while a dozen children are all jumping in at random intervals from every side. The sheer number of variables is incomprehensible. You would need to monitor in real time the magnetic field strength and stability of 12 different stars, each with its own personality. Some might be temperamental flare stars prone to daily tantrums of radiation, while others might be relatively placid, only to suddenly erupt with a once-in-a-century superflare when a gravitational nudge from a passing star twists its internal magnetic dynamo to the breaking point. The first step in any forecast would be an impossible one, creating a continuously updating three-dimensional map of the system's magnetic and gravitational topography, a task requiring computational power that borders on magic. And the chain reactions are where the forecast truly collapses into chaos. Imagine a powerful coronal mass ejection erupting from a star in the inner quadruple group. This isn't just a cloud of particles, it's a billion-ton projectile of magnetized plasma fired at a significant fraction of the speed of light. Your forecast would need to predict not only its path but its interaction with the environment. It might slam directly into the stellar wind of a neighboring star, compressing that star's magnetic field and triggering a secondary eruption there. Or it could miss the star itself but plow into a dense region of the system's shared dust cloud, creating a shock wave that accelerates particles to relativistic speeds, generating a sudden, system-wide spike in cosmic radiation that wasn't tied to any single star. An event on one side of the system could, within days or hours, manifest as a brilliant global aurora on a planet orbiting a star on the opposite side, with no obvious direct link between the cause and the effect. The weather doesn't travel in straight lines here. It ricochets, amplifies, and mutates as it navigates the labyrinth of competing stellar influences. For any potential inhabitants, this transforms space weather from an inconvenience into a constant existential threat. There would be no such thing as an all-clear signal. A planet might experience a period of relative calm, only for its atmosphere to be suddenly scoured by a radiation storm that originated from a stellar flare they couldn't even see, because the star that produced it was on the far side of their own sun. The very concept of a local star becomes meaningless when the radiation environment is a collective, system-wide condition. Building any kind of civilization would require living in perpetual hardened shelters. Surface agriculture would be impossible, routinely sterilized by ultraviolet and X-ray flux from unpredictable flares. Satellite-based communication and navigation networks would be rendered useless, their electronics fried by charged particles from a direction they weren't shielded against. Life would retreat underground or beneath planetary magnetic fields, with the weather report being the most critical piece of daily information, a complex, probabilistic nightmare that could never offer certainty, only a constantly shifting assessment of lethal risk. Now, as if the gravitational chaos and stellar fireworks weren't enough, astronomers have stumbled upon a discovery that adds an entirely new layer of mystery, one that whispers of powers operating in the shadows. Imagine making a detailed inventory of every single star in the system, calculating its size, temperature, and type, and then adding up the total energy output you would expect from this celestial family. You then point your most powerful telescopes at the system and measure the actual energy pouring out across all wavelengths, from radio waves to gamma rays. And the numbers don't match. The system is emitting significantly more energy than the sum of its 12 stellar parts. There is an unaccounted for surplus, a phantom energy source glowing brightly in the data, a signature of something powerful and hidden at work within the stellar labyrinth. The most immediate and scientifically compelling explanation points to a cosmic engine of immense power hidden in the darkness, accretion onto a compact object. Picture a stellar mass black hole, the remnant of a massive star that died long ago, silently orbiting within one of the system's outer hierarchies. It's not alone. It has a companion, a normal star that ventures close enough on its elliptical path for the black hole's monstrous gravity to begin siphoning away its outer atmosphere. This stolen gas doesn't fall directly into the abyss. Instead, it spirals inward, forming a vast, flat, superheated structure known as an accretion disk. The friction within this whirling disk of doomed matter is so intense that it heats up to millions of degrees, causing it to glow fiercely across the X-ray spectrum. This process converts gravitational potential energy into radiation with staggering efficiency, far outshining the star that is being consumed. From our distant vantage point, we wouldn't necessarily see the black hole or its victim star as separate points of light. We would simply detect this brilliant, persistent, high-energy X-ray glow emanating from a seemingly empty patch of space within the system, a ghostly beacon betraying the presence of the invisible predator. But a black hole isn't the only candidate. The same gravitational tides that stretch stars into ovals work their violent magic on planets as well, particularly gas giants. In our own solar system, Jupiter radiates more heat than it receives from the Sun, a relic of its ancient formation. Now amplify that effect 1,000-fold. Imagine a Jupiter-like world that has been captured into a crazily eccentric orbit, or one that is trapped in a relentless gravitational tug of war between 2 or even 3 of the system's stars. The changing tidal forces would constantly knead the planet's interior, flexing its entire structure. This friction generates immense heat, a process known as extreme tidal heating. The planet's core could become a furnace, causing it to swell and glow with a fierce infrared warmth, transforming it from a cold gas giant into a hot Jupiter, or even a superheated Jupiter, radiating far more energy than any star could provide through mere starlight. This planet would be a perpetual inferno, its atmosphere a churning maelstrom of storms driven by the immense internal heat, its infrared signature blazing like a cosmic bonfire and contributing significantly to the system's unexpected energy budget. Then there is the most speculative and frankly mind-bending possibility, one that takes us from astrophysics into the realm of advanced theoretical cosmology. What if this excess energy isn't natural at all? This is where we encounter the audacious idea of a type Roman III civilization on the Kardashev scale. A type Roman II civilization, which we might imagine, has learned to harness the entire energy output of its star, perhaps by building a Dyson sphere. A type Roman III civilization, however, is a galactic empire, a society that has achieved the ability to capture and utilize the energy of not just one star, but of all the stars in its galaxy. In a duodecuple system, a natural Dyson sphere equivalent is unimaginable. The complex orbits would tear any solid structure apart, but a type Roman III civilization might not build physical spheres. They might have mastered technology that allows them to directly siphon energy from stars in a more subtle, yet incredibly efficient way. They could be using methods we can barely conceive of, like creating artificial black holes as power plants, or directly catalyzing fusion in a star's corona to boost its energy output, or even tapping into the vacuum energy of spacetime itself. The observable signature of such an activity would be an energy profile that seems wrong. the light from the stars might contain unusual emission lines, suggesting elements or processes that don't occur in nature. The energy surplus might be focused and directed, rather than radiating uniformly in all directions, as if it were being beamed for a specific purpose. The sheer scale of the excess might be so colossal, so far beyond what even accretion or tidal heating could produce, that it defies all conventional astrophysical models. Of course, the scientific community rightly applies Occam's razor. The simplest explanation is usually the correct one. An accreting black hole or a tidally heated super-Jupiter are vastly more probable than a galaxy-spanning civilization. But the mere fact that we can look at a dataset, see an anomaly, and even entertain such a profound possibility is a testament to how these bizarre stellar systems push the boundaries of our imagination, forcing us to consider not just how the universe is, but what might possibly be within its most extreme and complex corners. The phantom energy source remains a tantalizing puzzle, a cosmic X on the chart that marks a spot where either nature is demonstrating a new form of its relentless power, or where, just maybe, we are seeing the faint, astronomical scale signature of intelligence operating on a level we can scarcely dream of. Indeed, if we step back from the intricate details of their chaotic orbits and stellar fireworks, we can perceive a Duodecuple star system not merely as a celestial curiosity, but as a colossal engine of cosmic evolution, a prolific factory whose primary export is diversity itself. Isolated single stars like our own Sun lead comparatively quiet, predictable lives. Their influence on the galaxy is largely limited to the light they emit and the handful of planets they might nurture. But a 12-star system is a fundamentally different kind of entity. It is a dynamic gravitational crucible that actively forges and ejects a stunning variety of cosmic objects, effectively seeding the wider galaxy with the raw materials and strange artifacts that isolated systems could never hope to produce. This relentless churning action makes them one of the universe's most efficient mechanisms for generating cosmic variety on a grand scale. Consider the process of stellar ejection. Within the crowded core of this stellar family, close gravitational encounters are a routine occurrence. These hyper-complex games of celestial billiards frequently result in one of the stars being flung outward at immense velocity, becoming a runaway star. These stellar fugitives, shot out of their birth system like a bullet from a cosmic cannon, carry with them a profound legacy. A massive, hot, O-type runaway star, for instance, will travel hundreds of light years before it explodes as a supernova. This means its cataclysmic death occurs not in the stellar nursery where it was born, but in some random, otherwise peaceful region of the galactic disk. The heavy elements forged in its core and during its violent death are therefore scattered far and wide, enriching vast tracts of the interstellar medium in locations that would have otherwise remained chemically pristine. This stellar diaspora, forced by the gravitational engine of the Duodecuple system, acts as a galaxy-wide fertilization program, ensuring that the elements necessary for future stars and planets are not locked away in dense clusters but are spread across the spiral arms, paving the way for planetary systems and potentially life in places that would have otherwise remained barren. The same gravitational slingshots that eject stars work even more efficiently on planets. For every stable world that manages to cling to an orbit in this maelstrom, countless others are violently evicted. This process creates a veritable fleet of rogue planets, dark worlds untethered from any sun, condemned to wander the interstellar void. While this seems like a bleak fate, it has profound implications for the galaxy's potential for life. A gas giant ejected from a Duodecuple system might drag along with it a family of large, icy moons. Shielded beneath a crust of ice and warmed by tidal forces and radioactive decay, these moons could maintain vast subsurface oceans of liquid water. Life could potentially arise and persist in these dark, isolated abysses, completely independent of starlight. The Duodecuple engine, therefore, isn't just scattering sterile rocks. It could be launching self-contained, life-bearing arc worlds across the galaxy, spreading the potential for biology to niches we are only beginning to imagine. These nomadic worlds become permanent additions to the galaxy's inventory, a hidden population of dark, free-floating habitats whose existence is a direct consequence of the gravitational turmoil within their prodigious birth systems. Furthermore, the intense environment within the system acts as a forge for stellar remnants that are far rarer in quieter neighborhoods. The frequent stellar mergers create blue straggler stars that appear paradoxically young and energetic. The relentless mass transfer in tight binaries leads to spectacular nova explosions and ultimately Type Ia supernova, the cosmic standard candles that allow us to measure the expansion of the universe. The gravitational stripping of stars by their companions creates exotic objects like hot subdwarfs, prematurely exposed stellar cores that defy standard classification. This system doesn't just contain stars, it actively manufactures stellar oddities. When the system eventually disperses or is disrupted, these uniquely processed stellar objects are released into the galactic field, enriching the diversity of the Milky Way's stellar population. A census of stars in our galaxy would show a certain percentage of blue stragglers and subdwarfs. A significant fraction of these almost certainly owe their bizarre existence to a past life within a complex, multi-star gravitational engine like the one we're describing. Finally, and perhaps most fundamentally, these systems are unparalleled chemical mixing vessels. The supernova that occur within them do not explode into empty space. They detonate in a medium already filled with the winds and radiation of a dozen other stars. The heavy elements they produce, the iron for future planets, the oxygen for future water, the carbon for future life, are immediately injected into this turbulent, shared reservoir. This enriched material is then swept up by stellar winds, incorporated into new generations of planets within the system, or even blown clear of the system entirely to seed nearby molecular clouds. A duodecuple system, therefore, acts as a rapid recycling plant for complex elements. It takes the primordial hydrogen and helium from its birth cloud and, through the violent lives and deaths of its massive stars, transmutes it into the heavier atoms of existence. It then mixes and distributes this enriched material with incredible efficiency, both within its own boundaries and out into the galaxy at large. In this grand cosmic cycle, these stellar families are not just passive inhabitants of the galaxy. They are active agents of its chemical evolution, driving the transition from a simple, pristine universe to one rich with the complexity required for planets, oceans, and life. From the surface of a world nestled within this stellar family, the sky would offer a spectacle of such overwhelming brilliance that the familiar concept of a starry night would be rendered utterly obsolete. Instead of a dark canopy dotted with distant, twinkling points of light, the heavens would be dominated by an unending, psychedelic light show, a lens flare apocalypse of cosmic proportions. The sheer number of suns, each a colossal engine of light, would turn the atmosphere into a permanent projector screen for complex optical phenomena. The air itself, filled with particles of dust and ice, would act as a gigantic, ever-changing lens, scattering and bending the light from a dozen different angles simultaneously. The result wouldn't be a simple, occasional glare. It would be a perpetual, shifting mosaic of halos, coronas, and radiant streaks that would wash out the faint background stars completely, making the very idea of constellations a forgotten memory. The source of this chaos is atmospheric scattering, the same effect that gives our sky its blue color and creates our stunning sunsets, but amplified to an almost ludicrous extreme. On Earth, we have one dominant light source. In a duodecuple system, a dozen suns of varying colors and intensities are all pumping photons into the atmosphere from different directions. Each sun's light would be scattered by air molecules, but because they are all different colors, some blazing blue-white, others glowing orange or deep red, the resulting sky color would be a chaotic, shifting pastel haze. There would be no single blue sky. Instead, the dome of the heavens would be a turbulent blend of hues, with regions of violet and cyan near the hottest stars, bleeding into areas of peach and salmon pink around the cooler ones, all blending into a general, luminous off-white glare that would make it difficult to look directly upwards for long. This isn't a sky you could comfortably gaze at. It's a sky that demands your attention with its relentless, multi-colored luminance. Then come the more structured optical effects, the halos and sundogs. On Earth, we see beautiful rings around the sun or moon when high-altitude ice crystals refract the light. Here, this phenomenon would be constant and mind-bendingly complex. With light arriving from multiple suns, each one would be surrounded by its own set of halos. But these rings wouldn't exist in isolation. They would overlap and intersect. Imagine a brilliant 22-degree halo from a blue-white giant being sliced through by the fainter, larger halo from a distant red dwarf. The sky would be filled with a web of luminous circles and arcs, a celestial Venn diagram written in fire. Sundogs, those bright spots that appear to the left and right of the sun, would also proliferate. But with so many suns, there would be sundogs everywhere, brilliant patches of intensified light scattered across the sky, their positions shifting as the suns move relative to each other and to the ice crystals in the upper atmosphere. It would be impossible to tell which bright patch of sky was an actual star and which was just a phantom created by the ice. The most disorienting effect of all, however, would be the constant, overwhelming lens flare. In photography, a lens flare is an artifact caused by bright light scattering inside a camera lens, creating streaks and polygons of light. On this world, the entire atmosphere, along with the eyes of any observer, would act as that flawed lens. Every brilliant sun, especially those low on the horizon, would project long, shimmering rays of light across the sky. These wouldn't be the gentle crepuscular rays we see at dusk. They would be glaring, sharp lines of radiance that could stretch from one horizon to the other. Because the suns are at different altitudes and azimuths, these flares would crisscross the sky in a dazzling, impossible-to-follow latticework of light. The visual noise would be immense, a permanent veil of glare that would obscure detail and make it difficult to focus on any single celestial object. For any nascent astronomers on this world, attempting to map the heavens would be a nightmare. The true positions and motions of the stars would be hidden behind this curtain of atmospheric distortion, their clean points of light smeared into a brilliant, confusing fog. The sky itself becomes the greatest obstacle to understanding the cosmos, a beautiful but impenetrable barrier of light forged by the simple, overwhelming presence of too many suns. Now, let's consider a puzzle that strikes at the very heart of physics, a paradox of energy and heat that challenges our understanding of how stars interact with the space around them. Each of these 12 stars is a colossal heat engine, converting nuclear fuel into radiation and hurling that energy out into the void. In a typical, isolated system, that heat radiates away cleanly into the cold, dark expanse of space. But here, in this crowded stellar metropolis, there's a fundamental traffic jam. The sheer volume of energy being produced within a relatively small volume of space creates a thermodynamic bottleneck, a situation where the system's ability to generate heat vastly outpaces its ability to shed that heat into the universe. Imagine a dozen industrial furnaces all operating at full blast inside a sealed warehouse. The air becomes superheated and the walls themselves begin to glow. This stellar family is trapped in a version of that very scenario, but on a cosmic scale. The inefficiency arises from a simple but profound principle. Radiation can only escape if it has somewhere to go. In the cold, empty space between most stars, infrared and other forms of radiant heat travel unimpeded for light years. But in the densely populated core of a duodecuple system, that escaping radiation doesn't find an easy exit. Instead, it slams into the stellar winds, accretion disks, and vast clouds of dust that fill the interstellar medium within the system. A photon of infrared light emitted from the surface of one star might travel only a short distance before being absorbed by a particle in the powerful wind of a neighboring star. That particle heats up and re-radiates the energy, but often back into the system, not out of it. This process, where energy is trapped and recirculated internally, turns the entire central region into a kind of thermodynamic oven, where heat is constantly being shared and reabsorbed rather than being allowed to dissipate. This leads to the counterintuitive and startling prediction. There could be vast regions within this system, particularly in the spaces between the innermost stars, that are significantly hotter than any standard stellar model would allow. We're not talking about the intense heat found on the surface of a star itself, but rather the temperature of what should be the empty space. In our own solar system, the space between planets is only a few degrees above absolute zero. But in the heart of this 12-star family, the ambient temperature in these shared zones could be thousands of degrees, hot enough to vaporize rock and metal instantly. This isn't a temperature you could feel, as there's no air to conduct the heat, but any object placed there would be bombarded by such intense infrared radiation that it would rapidly heat to incandescence. This creates an environment where the very concept of shadow is thermally meaningless. Even the dark side of a planet or asteroid would be baked by this all-pervading, superheated glow from the space around it. The consequences for planet formation and survival in these internal regions are catastrophic. The traditional snow line, the distance from a star where volatile compounds like water and ammonia can condense into ice, is completely scrambled. In this superheated interstellar medium, ices couldn't form at all, depriving budding planets of a crucial building block. Any pre-existing comets or icy bodies that strayed too close to the core would simply sublimate, their material adding to the dense fog of gas that further traps the heat. This creates a feedback loop. More gas and dust lead to more efficient trapping of radiation, which raises the ambient temperature further, which vaporizes more solid material, and so on. The system's core could become a self-insulating furnace, a place where the raw materials for small, rocky planets are continually being broken down and recycled, preventing the long-term stability required for a world like Earth to ever coalesce and cool. For the stars themselves, this thermodynamic entrapment has bizarre effects on their apparent life cycles. A star's outer layers, its photosphere, are in a delicate balance with the vacuum of space. But if the space around a star is already flooded with intense infrared radiation from its 11 siblings, that balance is disrupted. The star has to work harder to radiate its own internally generated heat outwards against this radiative pressure. It's akin to trying to shout in a room where everyone else is already yelling at the top of their lungs. Your voice is lost in the cacophony. This could cause the star's outer layers to become slightly more puffed up and extended than they otherwise would be, subtly altering its color and brightness as seen from afar. A star that should appear as a neat, compact sphere might instead look bloated and fuzzy, its visible surface artificially inflated by the thermodynamic struggle to cool itself in an already overheated neighborhood. When astronomers finally manage to translate the raw orbital data of a duodecuple star system into a visual map, the result is often less like a tidy diagram and more like a piece of abstract art flung onto a gallery wall. If you were to plot the positions and the looping, predicted paths of all 12 stars over thousands of years, you wouldn't see neat, concentric circles. Instead, you'd witness a sprawling, chaotic tangle of lines that weave around each other in patterns so intricate they defy simple description. This stellar cartography becomes a cosmic Rorschach test, a unique ink blot in the heavens where every observer, every scientist might see a different shape hidden in the gravitational noise. One might look at the tangled web of orbits and see a celestial dragon chasing its own tail. Another might perceive a vast, multi-lobed flower perpetually blooming and collapsing in the void. This isn't a sign of messy data. It is a direct and stunning visualization of the fractal-like, deeply chaotic nature of gravity itself when it's set loose in an environment of such overwhelming complexity. The universe, in crafting these systems, has become an expressionist painter, and the motions of stars are its brushstrokes. This artistic chaos emerges from a fundamental principle in physics known as deterministic chaos. The gravitational equations governing each star are, in theory, perfectly deterministic. If you knew the exact position, velocity, and mass of every single star at one moment in time, you could, in principle, calculate their future paths forever. But in a system with 12 massive bodies, this perfect knowledge is an illusion. The tiniest, most imperceptible fluctuation, a slight variation in the measurement of one star's velocity, a minute gravitational nudge from a passing rogue planet we didn't account for snowballs over time. This butterfly effect on a cosmic scale means that any attempt to project the system's future, even a few thousand years out, results in a wildly different picture each time you run the simulation. When you plot all these possible futures together, they don't converge on a single outcome. They branch out into a fractal canopy of possibilities, a visual representation of our fundamental inability to predict the long-term fate of such a complex dance. The ink blot we see is a map of probability, not of destiny. The fractal nature of these orbital plots is perhaps the most mathematically beautiful aspect. Zoom in on one small region of the map, say the space around one of the tight binary pairs, and you'll find a microcosm of the whole system's complexity. Their frantic dance creates a localized pattern of loops and walls that is itself infinitely detailed, resembling the self-similar patterns of a snowflake or a fern. Then zoom out to view the entire system, and you see that the grand, slow sweep of the outermost star's orbits is not a smooth curve, but a meandering, filamentary path that traces the edges of this same complex pattern. It's chaos, but it's chaos with a hidden order, a deep, structural resonance that repeats across different scales, telling us that the same simple law of gravity is generating this breathtaking complexity at every level, from the tightest binary to the widest stellar partnership. For the scientists studying these systems, this presents a unique psychological challenge. Interpreting the data is no longer a purely analytical task. It becomes an exercise in pattern recognition that is deeply subjective. Two astronomers looking at the same orbital simulation might propose entirely different hierarchical models based on what they perceive as the dominant structure. One might argue that the system is best understood as two sextuple systems in orbit, seeing a clear symmetry in the ink blot. Another might look at the same data and see a core of three quadruple groups, emphasizing different gravitational connections. The data itself is objective, but the story it tells is filtered through the human brain's innate desire to find familiar shapes in the noise. This makes the study of these systems as much about understanding our own cognitive biases as it is about understanding celestial mechanics. The cosmic Rorschach test reveals that when faced with the universe's ultimate complexity, science and art inevitably begin to merge, and our maps of the heavens become as much a reflection of our own minds as they are of the stars themselves. But as we try to peer into the future of such a system, we run headlong into a fundamental wall not of physics but of computation. The very same chaotic beauty that creates the cosmic Rorschach test makes these 12 star systems one of the ultimate challenges for modern science, a puzzle that pushes our most powerful supercomputers to their absolute breaking point. Imagine feeding all the data we have, the precise masses, positions, and velocities of a dozen suns, into the most advanced digital brain we can build. The goal seems simple: press a button and watch a simulation of the system's evolution over the next million years. Yet, the result is not a clear movie of the future, but a digital projection that inevitably and spectacularly shatters into nonsense. This isn't a failure of our machines or our code. It is a direct confrontation with the inherent mathematical chaos woven into the fabric of a complex gravitational universe. The root of the problem lies in a deceptively simple concept: rounding errors. In any computer simulation, numbers are stored with a finite number of decimal places. When calculating the gravitational pull between 12 stars, the computer is performing billions upon billions of mathematical operations. Each time it calculates a force, it makes an infinitesimally small rounding decision, perhaps truncating a number at the 15th decimal place. In a stable, predictable system like our own solar system, these tiny errors tend to cancel each other out over time. But in a chaotically unstable system like this one, they don't cancel, they amplify. Each small error slightly changes the predicted path of a star, which in turn dramatically alters the gravitational forces it exerts on its neighbors, which then magnifies the error in their path. This exponential growth of uncertainty turns the simulation into a runaway train of computational noise. A discrepancy smaller than the width of an atom in the initial setup can, over a few 100,000 simulated years, blossom into a prediction where one star is shown crashing into another when in reality it would have sailed peacefully past. The simulation doesn't just become inaccurate, it becomes a work of pure fiction, completely divorced from the reality it was meant to model. This phenomenon is a classic example of the n-body problem, and for 12 bodies, it is fundamentally unsolvable in the long term. Our supercomputers attack the problem with a technique called numerical integration, essentially breaking down the continuous flow of time into tiny, discrete steps. For each femtosecond of simulated time, the computer calculates the gravitational force on every star from every other star, then updates their positions and velocities. The computational cost is astronomical. Simulating just 1 year of this system's life can require more processing power than forecasting the global climate for a century. And even with all that effort, the result is only an approximation, a single possible timeline that is exquisitely sensitive to the starting conditions. To get any sense of the system's true potential futures, scientists have to run the simulation not once, but thousands of times, each time tweaking the initial data by a minuscule random amount. The result is not one future, but a vast probability cloud, a bundle of divergent pathways that shows every possible destiny, from stable resonance to stellar ejection, but cannot tell you which one will actually come to pass. This monumental challenge is, in fact, one of the most rigorous tests for the entire field of computational astrophysics. It pushes the limits of our hardware, demanding ever faster processors and more inventive parallel computing architectures. It also forges new software techniques like chain regularization, which cleverly simplifies the math for tight binary pairs to save precious calculation time. But more profoundly, it tests the very philosophy of our scientific models. We are forced to accept that for some systems in the universe long-term, precise prediction is simply not possible. Our knowledge has a hard expiration date. We can model the past and the very near future with stunning accuracy, but the further out we look, the more the universe insists on retaining its mystery. Studying a duodecuple system is therefore a lesson in cosmic humility, demonstrating that some of nature's most magnificent creations exist in a state of perpetual becoming, their futures unwritten and fundamentally unknowable, a beautiful testament to the infinite complexity that emerges from a handful of simple gravitational rules. And so we arrive at our final, and perhaps most humbling, discovery that this seemingly impossibly complex family of 12 stars is not the ultimate expression of cosmic chaos, but rather a gentle, miniature preview of the true maelstrom that lies at the very heart of galaxies. The environment we've been exploring, with its gravitational pandemonium, frequent collisions, and stellar ejections, is not unique. It is simply a scaled-down, local model of the unimaginable violence that unfolds in the galactic core. At the center of our own Milky Way, and indeed most large galaxies, resides a supermassive black hole, a gravitational monster containing the mass of millions, even billions of suns. And around this cosmic abyss, stars are not spaced by light years. They are packed together in a frantic, densely populated stellar city, a realm where the conditions of a duodecuple system are not an anomaly but the norm. Think of the core of our galaxy, a region known as Sagittarius, a star. There, within a space that would fit comfortably inside our solar system, thousands of stars are crammed together in a swirling, high-speed dance around the central black hole. The average distance between these stars is a tiny fraction of a light year, in some cases just a few times the distance between our Sun and Pluto. This is the duodecuple system's environment writ large, a place where gravitational interactions are not rare events but constant background noise. The same processes we see in our 12-star family tidal stripping, stellar collisions, the creation of runaway stars, occur here on an industrial scale and at a ferocious pace. By studying the comparatively simple and nearby dynamics of a system like TYC 7037-891, we are essentially running a controlled laboratory experiment, allowing us to develop and test the mathematical models we need to understand the far more extreme and distant chaos of the galactic center. The presence of the supermassive black hole adds a terrifying and dominant new force to the equation. Its gravity dictates the rhythm of the entire core, forcing stars into incredibly tight, fast orbits. Close passes that would be noteworthy events in a duodecuple system are a daily occurrence here. This relentless gravitational stirring prevents stars from settling into quiet, long-term orbits, ensuring the environment remains perpetually violent. Stars are whipped around the black hole at percentages of the speed of light, and when two of them interact, the slingshot effects can be far more dramatic. A star ejected from the galactic center isn't just cast out into the galactic disk. It can be flung clear out of the galaxy entirely, becoming a hypervelocity star, a true interstellar fugitive on a one-way trip into the void of intergalactic space. The duodecuple system teaches us the rules of gravitational billiards. The galactic center shows us those rules applied with universe-shattering force. This comparative study offers profound insights into one of the most energetic and mysterious phenomena in the cosmos: active galactic nuclei and quasars. These are galaxies whose cores are so phenomenally bright they can outshine the rest of the galaxy combined, powered by the accretion of vast amounts of gas onto the central supermassive black hole. But where does all this gas come from? The answer likely lies in the very stellar dynamics we see in miniature in multiple star systems. In the densely packed core, the frequent collisions between stars don't just create new stars, they also shred stellar atmospheres, releasing immense clouds of gas. The powerful stellar winds from thousands of hot, young stars, all blowing in a confined space, create a pressurized, turbulent medium. This constant grind of stellar interactions acts as a universal food processor, churning out a continuous supply of gas that then spirals in to feed the insatiable appetite of the central black hole, lighting up the quasar. By observing how stellar winds and collisions manage and redistribute material in a duodecuple system, we can better understand the feeding mechanisms of these cosmic monsters. Ultimately, the journey through these 50 strange discoveries brings us to a powerful and unifying conclusion about the cosmos. From the intricate dance of a dozen stars to the frantic whirl of a galactic core, the same fundamental laws of physics are at work. Gravity is the great sculptor, and chaos is its primary tool. A duodecuple star system is a cosmic bridge, connecting the familiar dynamics of our own stellar neighborhood to the most extreme environments the universe has to offer. It demonstrates that complexity and chaos are not exceptions, but are fundamental features of a universe that is dynamic, interconnected, and constantly in flux. By learning the language of these 12 sun families, we are learning to read the story of the universe itself, a story written in the gravitational bonds between stars from the smallest cluster to the very heart of the galaxy. So as we pull our gaze back from this gravitational whirlwind of 12 suns, we find our own perception of the cosmos irrevocably altered. We have journeyed through a realm where gravity is not a gentle guide but a chaotic artist, where stellar zombies are resurrected in violent explosions, where planets are cast adrift into the eternal night, and where the very fabric of time twists and slows under the weight of so many stars. The 50 discoveries we have explored are not merely a list of facts. They are a testament to a universe that thrives on complexity and defies our simplest intuitions. These systems are more than just celestial curiosities. They are the ultimate natural laboratories, offering us a front row seat to the most extreme processes of stellar birth, life, and death. In their intricate dances, we witness the forging of elements, the acceleration of particles to unimaginable energies, and the constant dynamic struggle between order and chaos that shapes the entire galaxy. They remind us that our own quiet solar system, with its single reliable sun, is but one peaceful province in a cosmos teeming with stellar metropolises. The universe is not just stranger than we imagine. It is, as J.B.S. Haldane once noted, stranger than we can suppose. And with every new telescope, every advanced algorithm, and every burst of human curiosity, we peel back another layer of that magnificent strangeness. So we turn the question over to you, our fellow cosmic explorers. What other secrets do you think are locked within these multi-star maelstroms? What wild theories do you have about the possibilities for life or the ultimate fate of these stellar families? Let us know your thoughts in the comments below, and don't forget to subscribe for more journeys into the deepest mysteries of